Hello, Sébastien.
Hello.
Hi.
Hi, Violeta.
Ready?
Yes, we are just waiting, Alessandro.
So how is it in Brazil?
Sorry?
How is it in Brazil now?
This is always a difficult question.
Hello.
Hello,
Can you see
Alessandro.
me? Yeah, okay. Sorry for the delay. I couldn't find the link anymore and it took a little while to enter.
Well, let's we allow everybody share. One moment. Okay. Okay, it seems that you can share your screen if you want.
Okay, yes. Okay, and oops. Okay, can you see it?
Yes.
Okay, good.
So we can start?
Yes, just a second. Okay. Okay, so shall I start? Yes.
Okay, so welcome everybody. So I would like to thank the speakers which accepted to participate of this mini workshop. And our first speaker is Alessandro Giuliani from University of Roma and Centro Linceo Interdisciplinare.
Beniamino Segre.
Thank you. And he will speak about scale limit and finite size correction of 2D non-planar Ising models. So it's with you, Alessandro.
Thank you very much. Thanks, Rodrigo, for organizing this nice mini workshop and for the possibility to present my results here. Yes, today I will review some results obtained in the last few years on scaling limit and finite size corrections in non-integrable perturbations of the two-dimensional Ising model at the critical point. And this review is based on joint works with Giovanni Antinucci, Rafael Greenblatt, and Vieri Mastropietro. So let me start with an introduction and an overview of the problem. So the long-term goal that I would like to understand. So this is a big open problem in mathematical statistical mechanics is to prove existence of the scale limit of the Gibbs measure of statistical mechanics models at criticality and characterize the nature of this scale limit. In particular, this characterization should substantiate the so-called universality hypothesis for the scale limit. which is a very strong form of independence of such scale limit from the microscopic details of the Hamiltonian defining the statistical mechanics system. So the reason why one believes that the scale limit, besides existing, should be universal, in a sense to be clarified along the way, is based on Wilsonian renormalization group. So Wilsonian renormalization group is a procedure, if you like, an algorithm that in its original version is at least partly heuristic, that allows one, starting from a given microscopic Hamiltonian, to construct, after appropriate tuning of the critical temperature, to construct the scale limit as the fixed point of a suitable transformation, the so-called Wilsonian renormalization group transformation. This Wilsonian renormalization group transformation consists in integrating out degrees of freedom at a given length scale. And after this integration, it consists in applying a rescaling of the distances, so that at each step you're back to a system with standard unit length equal to whatever, 1, say. The fixed point constructed in this way, at least I understand that this is vague at this level, but there is a concrete procedure to define this RG step. The fixed point of this procedure is automatically scale invariant and is presumed to be to correspond to the scale limit of a large class of microscopic Hamiltonians. Under mild additional hypothesis, this fixed point, besides being scale invariant, is expected to be conformally invariant. And this observation, that is originally due to Polyakov, allows one to use the methods nowadays known as methods of conformal field theory, to use these methods to classify all possible fixed point of the renormalization group map. So somehow to have a systematic procedure to classify all possible scale limits of given microscopic Hamiltonians. It's remarkable that in particular in 2 dimensions, the set of possible conformal invariant fixed point is relatively small. And if one believes in all this picture, given a microscopic model, what you're left to do somehow is to identify what is the correct conformal field theory that this microscopic model should scale to under the scale limit procedure, or if you like, this iterative application of Wilsonian renormalization group. Okay, this picture that I don't pretend is completely clear if you never saw it before, but I mean, this is if you like a vague overview of the reason why we believe critical statistical mechanics model to define conformal invariant and universal scaling limits. This picture is conceptually very satisfactory and widely accepted, but the truth is that there are very, very few cases in which this has been substantiated mathematically. I mean, for sure, there is no mathematical confirmation of the full picture, but even partial aspects of this picture are very hard to prove mathematically. The challenge, the goal would be to prove via Dirsroot universality of large classes of microscopic families of microscopic Hamiltonians with explicit identification of the scale limit and explicit proof that this scale limit is conformally invariant as expected. Okay, so even if the big picture is still far from being fully proven, in the last few years there has been progress on understanding of universality of non-integrable two-dimensional models, at least certain class of non-integrable two-dimensional models, including in particular certain non-planar deformations of the Ising model and certain classes of perturbations of two-dimensional dimer models. Today I will focus on the progress that has been made on non-integrable deformations of two-dimensional Ising models at the critical point. So let me define more precisely the setting. Let omega be a finite simply connected domain of the plane. So in this picture, it is this potato-like domain. Let A be the lattice spacing and omega A the discretization with lattice spacing A of this domain omega. So it's a graph whose vertex set is the collection of sites of the square lattice with lattice spacing A contained in this omega. And you can take for edge set, for instance, the set of nearest neighbor edges. For the incoming formulas, this is not particularly important. In certain situations in the following, I will keep A fixed and I will send omega to the full plane, or vice versa, I will fix omega and send A to 0. Okay, on this on the vertex set of this omega A, I will define an Ising Hamiltonian of the following sort. So this Ising Hamiltonian has first term, which is the usual nearest neighbor interaction of the form minus j sum over nearest neighbor sites of sigma x, sigma y. Here, sigma x and sigma y are Ising spins that which can take values plus minus 1. This j, you can take any positive value. For instance, j equal 1 is not particularly important. So if we stop here, this would be the regular nearest neighbor Ising model, but I will consider a family of Hamiltonian of Ising Hamiltonians obtained by adding to this term here an additional term of strength lambda, which in general breaks planarity of the model. So this term is not restricted to nearest neighbor pairs, and it breaks integrability even more importantly. The two things are connected, of course. So this term here, in this term here, I'm summing over subsets of omega A. Sigma of the subset capital X is just the product of the spins at the sites of capital X. V of capital X is a finite range, translational invariant, even interaction. So, for instance, you can imagine that V of X is supported on subsets of omega A of cardinality 2, in which case this represents a pair interaction that in general will not be nearest neighbor. So in that case, if we restrict to V of X supported on sets of cardinality 2, this describes an Ising model with pair interaction, but not necessarily nearest neighbor. We actually don't need the condition that this is a pair interaction, so we can take this interaction to include quartic terms, sextic terms, and so on. The important thing is that this is an even interaction, so with the same parity property under spin flip as the first term. So we don't include terms that are of order 3, 5 in the spins. This lambda is a parameter that you should imagine, that you should think of as being small compared to this j. Okay, so And then for the moment, we allow generic boundary conditions. Then later we will be more specific. In particular, you can think for the moment that boundary conditions are open or plus or minus, or if omega is a square or a rectangle, you can also allow periodic boundary conditions. Still at the level of definitions, I will denote by mu of A the Gibbs average of the observable A. The Gibbs measure is, as usual, the probability measure with weight proportional to e to the minus beta h. This average symbol mu, I attach to this average symbol mu a number of labels recalling, so there is a lambda recalling that there is this interaction term here, this additional non-nearest neighbor interaction here. Beta recalling the value of the temperature, A recalling the value of the lattice spacing, and omega labeling the domain in which on which the model is defined. Okay, so the model is well known to display phase transition. So for instance, if you take A fixed, so if you take fixed lattice spacing, say 1, and you send omega to the full plane, it is well known that for small enough beta, there is a unique infinite volume Gibbs state with exponentially decaying correlations. For large enough beta, if lambda v is a ferromagnetic pair interaction, or if lambda is sufficiently small, it's known that there are two distinct pure states with non-zero magnetization and exponentially decaying truncated correlations. So these informations come from, for instance, from cluster expansion. Additionally, if lambda v is a ferromagnetic pair interaction, maybe even more generally than this, but certainly if it's ferromagnetic pair interaction, there is a unique value of the inverse temperature called the inverse critical temperature, beta c, that in general depends on lambda, separating the two phases. Okay, what happens at this critical temperature? What is expected, and as far as I know, it's not known in general, is that if lambda v is a ferromagnetic pair interaction, or for more general v's and lambda small enough, it is expected that there is a unique critical infinite volume Gibbs state, denoted by this this symbol here, characterized by polynomially decaying correlations. This is for sure known if lambda is equal to 0, so for the standard two-dimensional Ising model, but it is expected much more generally. Not only that, there is from the Wilsonian RG picture plus the CFT classification that I mentioned at the beginning, there is a very precise, there are very precise conjectures about the properties of this critical Gibbs measure. So I will, in the next couple of slides, I will recall some of these very remarkable conjectures that one is led to on the basis of the universality picture that I vaguely mentioned at the beginning of my talk. So this is these are some of the properties that are expected for the critical theory. So fix beta to equal to this critical temperature, fix the domain omega as you like, and rescale the spin variables as follows. So take the spin observable sigma x and rescale it by this a to the minus 1/8. This will be the spin field at x. And rescale the product of two neighboring spins in the following way. So multiply by a to the minus 1 and subtract the average of this product of two neighboring spins, which is non-zero. So this rescaled combination of the product of two neighboring spins is called the energy field at x. compute the average at the critical temperature, compute the average of any mixed correlation of spin field and energy field, and then take the limit a to 0 at so 0 lattice spacing and at fixed omega. So it is expected that this limit should exist, and not only should exist, but it should be extremely explicit and with a number of remarkable properties. In particular, the limit is expected to be independent of lambda up to a finite multiplicative renormalization. So this should be equal to a prefactor, depending on which may depend on lambda, and depending on how many spin field insertions you have and how many energy insertions you have. Once you factored out this prefactor, what you're left with is a non-trivial function of x1, x2, xn, y1, ym, which is expected to coincide with the multi-point correlations of the minimal CFT model with central charge 1 alpha. And these correlations are explicit and well known. And in particular, the correlations of this conformal field theory model should be conformally covariant under Riemann mapping of the domain. So if you map omega to omega prime under a Riemann mapping, the value of this correlation should be modified accordingly. Should be the image, an appropriate image of the correlation in omega prime should be an appropriate image of the correlation in omega obtained by applying the Riemann mapping from omega to omega prime. There is an explicit formula once again that allows you, once you know the Riemann mapping and the correlations in omega, allow you to compute the correlation in omega prime. So thanks to this explicit formula, correlations in any domain can be obtained from those for instance, in the half plane, which are particularly. So correlation in any domain for any value of lambda for which all these pictures should be valid can be obtained from those of the non-interacting of the planar Ising model in the half plane, which are easier to obtain and pretty explicit. Okay, so this is if you like, a family of remarkable implications of the universality pictures I mentioned at the beginning. Let me mention another kind of remarkable prediction, which concerns the so-called universal the universal oops, I think I have a wrong version of the seminar. I made them. Let me see. Yes, I'm sorry. I produced just in the right before the seminar a version without the pause command, which was not very appropriate for the tablet. But then I think I used the wrong version. Sorry. So let me proceed with the hopefully correct version. So here are the predictions about the so-called universal finite size corrections to the critical free energy. So predictions are as follows: fix once again beta equal to the critical, the inverse critical temperature. Fix the domain omega as you like, and compute the free energy asymptotically as a to 0 in the following form: as a term diverging as a to the minus 2 in the limit a to 0, plus a term diverging as a to the minus 1, plus a subdominant term, which I call C omega of A and lambda. This depends on the shape of the domain omega. It depends on the lattice spacing. It depends on the choice of the interaction of the non-planar perturbation lambda B. Okay, these first two terms are known or expected to be of the following form: a to the minus 2 times the area of the domain times a function f of lambda, which is independent of omega and a. This is the specific bulk free energy. This second term is known or expected to be of the form a to the minus 1 times the length of the boundary of omega times the surface tension tau of lambda, which is independent of omega. This subleading term is expected to have remarkable universality properties. The way in which it scales with respect to A, it depends on whether the so-called Euler characteristics or Euler number, chi, is equal or different from 0. So this Euler characteristics is this combination here, is 2 minus twice the number of handles minus the number of boundary components. So if you have a simply connected domain with open boundary conditions, this chi is equal to 1, is 2 minus 0 minus 1 equal 1. If you have a torus, this is equal to 0, 2 minus 2 minus 0. If you have a cylinder, this is 2 minus 0 minus 2 is again 0. So if this Euler characteristics is different from 0, so for instance, in the case of the simply connected, a finite simply connected domain with a single boundary component, the prediction is that this C of omega scales logarithmically with A as A to 0, with a very explicit prefactor, which is minus 1/6 the value of the central charge of the underlying CFT conformal field theory described in the scale limit. In the case of the Ising model, C is equal to 1 alpha, times the Euler characteristics. So if you take the Ising model in a generic finite simply connected domain, this should be minus 1/12. This prediction for generic conformal field theory this formula has been proposed by Cardi and Peschel in 1988. If chi is equal to 0, then this subdominant term is expected to scale to go to a constant as A to 0. This constant is expected to be independent of lambda, exactly as this combination here. But in general, it will depend on the shape and topology of omega. For instance, if you take omega to be a torus with aspect ratio xi, the prediction is that this C0 of omega is this specific combination of Jacobi theta functions computed at e to the minus pi xi, where xi is the aspect ratio of the torus. And there are similar predictions for the cylinder, for instance. Okay, so both this prediction here and the prediction about the structure of the correlation function I mentioned earlier are largely unproven. Here, let me also observe, which is something that, well, depending on your background, you may find more familiar or as unfamiliar as this, is that in the limit in which the aspect ratio of the torus tends to infinity, so if you take a very thin and long slice, a very thin and long torus, this combination of Jacobi theta functions becomes simply the value of the central charge, 1 alpha in the case of the Ising model, times pi over 6 times the aspect ratio itself. So for if you are interested in computing the central charge of the model from this subleading corrections to the free energy, you can just look at the asymptotics in psi of this subleading term here. So the central charge can be read from the prefactor in front of psi. Okay, both this prediction about these subleading corrections to the critical free energy and predictions about the correlations, the scale limit of the correlations at the critical point are largely unproven. Universality in lambda and in the choice of V is in general open, there is, I think, it would be extremely interesting to substantiate the full picture here. What I would like to review today is partial progress in the understanding of this picture. In particular, constructive renormalization group methods allowed us to prove some aspects of this picture. In particular, if omega is a straight cylinder, we succeeded in constructing the scale limit of the multi-point energy correlations. As a special case of, so we can construct the scale limit for any straight cylinder with any aspect ratio, any value of the sides L1, L2. So from this construction, we obtain in particular the case of the half plane and of the full plane. Concerning the computation of the subleading corrections to the critical free energy, we proved that if omega is a torus with aspect ratio psi, the subleading correction to the free energy behaves asymptotically as the aspect ratio to infinity as pi over 12 times psi. So we proved that the prefactor in front of this value of the aspect ratio is independent of lambda and matches with the expected value of the central charge from the CFT prediction. As I will try to stress in the following, this second result here about this universality of the subleading correction in this limit of large aspect ratio of the torus was proved earlier than the recent construction of the energy correlations in the cylinder. And actually, we employed a method that was a bit more primitive than the one we developed in the last couple of years. So actually, the proof, the construction of the energy of the scale limit of the energy correlation in the cylinder forced us to understand the effect of finite size corrections at a precision that I'm sure will allow us to compute at a better precision the universal finite size corrections as well. I mean, I just didn't have time to recheck all the details, but I'm pretty optimistic that now that we have in our hands this improved method to compute the scale limit in domains with boundaries, we will be able to compute boundary critical exponents for models of the class I described, both in the cylinder and in the rectangle. And we will be able to compute the full form of the subleading correction to the free energy in tori, in infinite tori, infinite cylinders, and presumably, but this I see this as a more difficult problem, presumably also the prefactor in front of the logarithm of in the subleading correction to the critical free energy in rectangles. Okay, so once again, this is an anticipation of what we really did so far, but I'm optimistic that the methods we developed for the first item here will allow us to prove more refined formulas also for the second problem, the one of the universal subleading corrections to the critical free energy. Okay, so in the following, so this is a long overview and anticipation of our main results. In the following, I will try to state more precisely our main results, but before doing that, also in order to contextualize more precisely our technical statement of the results, I will make a small detour / review of the exact solution of the nearest neighbor Ising model. So let me discuss some key aspects of the exact solution of the nearest neighbor Ising model. So this is, if you like, the special case of the class of Ising Hamiltonians I consider so far, in the case that lambda is equal to 0. So the Hamiltonian for lambda equal to 0, the Hamiltonian reduces to the usual minus j sum over nearest neighbor sites sigma x sigma y. As well known in 2 dimensions, this model is exactly solvable, and the solution is due to infinitely many people, in particular on Sager, Kaufman, Young, Castelline, Katz and Ward, Montrol, Potts and Ward, Schultz, Lieb and Mattis, McCoy and Wu, Tracy, Baruch, Perk, Kadanoff and Cheva, and so on. So the list of people who contributed to the exact solution is very, very long and continues until nowadays. I mean, the work of Onsager dates back to the 40s, but people still continue to work on the exact solution of the Ising model, and there has been remarkable progress on the matter even in the last few years, as I will discuss in a moment. So what does it mean that the model is exactly solvable? So it is exactly solvable in a very strong sense. So for instance, if you fix the lattice spacing and you send the domain to infinity, you can get closed formulas for the free energy, for the specific heat, for the magnetization, and for the energy and spin correlations. The closed formula for the spin correlations require, at least if you want explicit asymptotics, they require the choice, a specific choice of the location of the points where of the points at which you compute the spins. So let me, and from these formulas, of course, you can even you can also compute the scale limit as a to 0 after appropriate rescaling of the spin and energy observables. So let me be more precise. So fix beta c to the lambda equals 0 value of the critical temperature, which is known to be this explicit number here. Send first omega to infinity and then lattice spacing to 0 after appropriate rescaling of sigma and epsilon. So let me recall. Oops. Yeah, let me recall that the rescaling in A of the spin observable and of the energy observable are these ones. So compute the average of the spin-spin correlation with this a to the -1/8 rescaling, then send a to 0. From the exact solution, you find this remarkable formula for the spin-spin correlation. You get A, where A is an explicit number defined in terms of an integral of a special function, divided by the distance to the 1/4. As for the energy correlation, in the same limit, you get 1/π², 1/distance squared. More in general, the endpoint energy correlations are obtained quite straightforwardly from the exact solution, and they take the following form. They take the form pi to the -n times the absolute value square of the Pfaffian of a suitable antisymmetric matrix whose entries depend on the locations x1, xn of the energy fields. So this antisymmetric matrix is nothing but the matrix that is 0 on diagonal, and off diagonal is 1 over Zi minus Zj, where Zi is the complex representative of the point xi, of the complex of the point xi. It's not so important that you absorb the details of this formula, but the message is that from the Onsager's exact solution, there is a very explicit formula that you obtain for the energy, for the multi-point energy correlations in the plane that was known since forever, somehow, since the 40s, I think. The story for the spin correlations is more intricate. Already the computation of the spin-spin correlations required some care, and the multi-point spin correlations, the formula for the multi-point spin correlation took a lot of years to be fully proven. It was proved in around 2012 independently by Dubeda and by Chelkak, Ongler, and Izurov. It takes this form here in the infinite plane, in this scale limit in which you first take omega to infinity and then a to 0. So this is the formula for, if you like, the scale limit in the full plane. And Chelkak, Ongler, and Izurov, using methods developed by Smirnov, Chelkak, and Smirnov, Ongler, managed to also to compute the scale limit of the spin correlations in generic domains of the plane. So they proved in particular that in a generic domain, the scale limit of the spin correlations can be obtained via Riemann mapping from those in the half plane. And those in the half plane can be are given by an explicit formula similar to this one, obtained by generalizing this one via a suitable image method. And also the multi-point energy correlation, this is even easier, can be computed a posteriori, now are known even in generic domains, not necessarily in the plane. So somehow the order in which I presented here the results are a bit are partially historical. So first, correlations have been computed in the full plane. The energy correlations for 2 points or n points were computed easily on the basis of Onsager's solution. The 2-point spin-spin correlation were computed with a more difficult method, but already in the 50s, 60s, and generalized to generic number of points much more recently. And even more recently, it was proven that the generalization of these formulas to generic domains of the plane. So this is somehow these are somehow some key aspects of the solution of the Ising model from a modern perspective, if you like. Now that I described these results for the lambda equals 0 case, sorry, and this is about correlation. What about the finite size corrections? Okay, here, even in the lambda equals 0 case, situation is not so well developed as far as I know. So if omega is a torus, there is an old computation due to Ferdinand and Fischer dating back to 69, where they computed the subleading correction of order 1, which is given by the combination of the Jacobi theta function that I showed before. The main term with f infinity, this combination of logs, was computed originally by Onsager in 44. So the novelty of the Ferdinand Fischer computation is the computation of this order 1 term. This term here that Ferdinand and Fischer computed, if you like, blindly from Onsager's solution, was rederived via CFT methods by Di Francesco, Saleur, and Zuber in the mid-80s. So they actually showed that if you start from the minimal model with central charge 1/2, just on the basis of modular invariance, you can guess that the universal finite size correction should be precisely this special combination of Jacobi theta functions. If omega is a finite simply connected domain, the prediction of Cardi and Peschel is that the subleading term should be -1/12 logarithm of a to the -1 times the length of the boundary of omega. Surprisingly, this formula is, as far as I know, unproven for a domain of generic shape, and it has been proved only in the case that omega is a rectangle. And as far as I know, it has been proved very recently in a series of 2-3 papers by Hatch, dating the first one of which came out in 2017. At least I didn't find references, all the references with proof of this formula. So, even in the case of the integrable Ising model, there is plenty to do, if you like, to substantiate the conjecture about the subleading universal, presumably universal subleading correction to the critical free energy. Let me stress that the computation, this computation by H, in the case that omega is a rectangle, is related and more complicated than to a similar computation by Duplantier-David that they performed for the discrete Gaussian free field in rectangular domains. So in 89, I think, Duplantier-David computed the analogous logarithmic correction for the discrete Gaussian free field in rectangular domains and proved the analog of that formula there. So the computation in the Ising model is a sort of complication of that, but morally it is similar. Unfortunately, the way both Duplantier-David proved the result and H proved this result, the computation is blind, a bit like Ferdinand Fischer one. So it's really based on computing the asymptotics of certain terms in the Sager solution, and but there is no clear reason why the same proof should be valid in generic domains omega. Okay, so this is this was a brief review of certain selected results of the nearest neighbor Ising model, and now I'm ready to state our main results for the case of the non-planar Ising model. So the class of deformations of the nearest neighbor model obtained by adding this term in which lambda is sufficiently small, V is finite range translational invariant even interaction. So let me first state our main result for the scale limit of the multi-point energy correlations. So to formulate it in a slightly simpler, more readable form, let me assume that V of x is rotation symmetric, but this is not really needed. We can drop this assumption at the cost of having a slightly more complicated expression here. So it takes V of x to be finite range, translational invariant, rotation symmetric, and even interaction, lambda small enough compared to J. Take omega to be a cylinder of sides L1, L2 with periodic boundary conditions in the horizontal directions. There exists a value beta C of lambda playing the role of interacting critical temperature, a critical temperature for this model, for this lambda dependent model, and and the function z of lambda, both beta C of lambda and z of lambda are analytic in lambda for lambda sufficiently small, such that for any n larger than 1, the endpoint energy correlation the scaling limit of the endpoint energy correlation computed at interaction lambda and temperature beta C of lambda is equal to the following expression. So there is a prefactor z to the n, where z once again is an analytic function of lambda, equal to 1 when lambda is equal to 0. So z of 0 is equal to 1. So there is this multiplicative prefactor, and modulo the multiplicative prefactor, the value of the scale limit is this minus 1 to the n over pi to the n times the Pfaffian of this explicit antisymmetric matrix. And this G seal is just an explicit expression independent of lambda. Specifically, is a sum over images of this homogeneous function here. If you're interested, the specific sum over images that we need, that we obtain is this one, but is not very important. So the message is that the scale limit is extremely explicit. It is the same as the one you obtain for lambda equals 0, modulo the presence of this z to the n. When lambda is equal to 0, this z reduces to 1. In general, is 1 plus order lambda, and it is what it is. Okay, so somehow this is provides a full construction of the scale limit of the energy sector, as they call it in the CFT language, for this this family of microscopic Hamiltonians. And we have, in fact, this strong universality properties that the scale limit is independent of lambda modulo the presence of this multiplicative prefactor. A few remarks. So for this, for the validity of this result, we don't need lambda and v to be positive. So we don't need interaction to be ferromagnetic. As I mentioned, rotational invariance is unimportant. So we can drop this assumption at the cost of having a slightly more complicated expression for the scale limit. Still, it is very explicit. So the theorem is formulated for the critical case, but the method of proof allows us also to control the so-called massive scale limit. So we can take the temperature, instead of being exactly equal to the critical temperature, we can also take it to be the critical temperature plus order A. In this case, the interacting, so we get once again an explicit formula for the scale limit, but the scale limit now involves a propagator that rather than being of the form 1 over being homogeneous and decaying like 1 over distance, is exponentially decaying with a mass that is proportional to the coefficient in front of A here. If beta differs from the critical temperature order 1 rather than order A, then the proof is extremely easier, and we find that at finite A, the correlations decay exponentially with a correlation length proportional to A. Notice that even if our methods allow us to get this result here very easily, standard cluster expansion methods don't provide such exponential decay uniformly in the distance from the critical temperature. Here we have a very fine control of the energy correlations at the critical temperature, very close, order A close to it, and of course, if you like, order 1 close to it. The bounds we get are uniform in the sides of the cylinder. In particular, we can take L1, L2 to infinity, and depending the way we do it, we can obtain from the theorem the correlations in the full plane and in the half plane. The case of the full plane is substantially easier than the others due to the lack of a boundary. The presence of a boundary creates a lot of complications in our construction. The case of the scale limit in the full plane was studied earlier by myself, Greenblatt, and Mastropietro in 2012. And in order to go from our construction in the full plane to the one on the cylinder, we had to overcome a number of technical complications due to the presence of the boundaries. And as I mentioned earlier, the technical improvements we introduced to deal with the boundaries should allow us now to compute more refined formulas also for the universal finite size corrections. Even if I didn't state it explicitly, our method of proof also provides bounds on the speed of convergence of the lattice endpoint energy correlations to their scale limit. So we actually have formulas. Okay, if you want, I can show you later on the difference between the finite A correlation and the scale limit. Okay, the proof can be generalized to the computation of boundary spin correlations and boundary energy correlations. We are actually in the process of writing the proof down for the boundary spin correlations. And the result on the boundary spin correlations is related to a result obtained quite recently by Eisenman, Dumil, Kopenta, Sion-Varzel via completely different methods of random currents representation and Russo-Simul-Welsh bounds for the random currents. Using these methods, Eisenman, Dumil, Kopenta, Sion, and Varzel proved that boundary spins in the half plane are asymptotically Pfaffian as A to 0. In the case that lambda v is a ferromagnetic pair interaction. So they need, so the limitation of the result is that they need lambda v to be a ferromagnetic pair interaction. And they prove that the scale limit is a Pfaffian, but they don't characterize the entries of the matrix of the Pfaffian. On the other hand, it's very remarkable that the result is valid for generic values of lambda, even very big. So the result is non-perturbative. While our theorem requires lambda to be sufficiently small, for them lambda can be 1000, whatever. Okay, given the fact that I just have 5 more minutes, I guess that the part of the seminar I prepared on the sketch of the proof will have to be skipped. So let me just mention a few very vaguely the method of proof. The proof is based on a representation of the generating function of energy correlation in the form of a non-Gaussian Grassmann integral, and in a multi-scale computation of this non-Gaussian Grassmann integral that is reminiscent of the multi-scale methods that in the community of constructive quantum field theory have been used to study phi-4 in 2 dimensions or in 3 dimensions. We employed this strategy and this method to first in 2012 to compute the scale limit of the energy correlations in the full plane, as I just mentioned. But that proof used translational invariance too heavily. We needed it in order to guarantee that the quadratic part of the effective action is explicitly diagonalizable at all RG steps. And in order to guarantee, even more importantly, that the effective couplings at all steps are constants rather than functions of the position. The presence of boundaries creates problems for both these aspects. So in order to allow for the presence of boundaries and to get a refined control on finite size corrections, we had to introduce a bulk edge decomposition of all the contributions to the generating function of the correlations, and to prove that the edge contribution has an improved scaling dimension as compared to the corresponding bulk operators. Via this decomposition, we managed to control the finite size corrections in terms of the flow of a so-called of an additional boundary marginal coupling, and the flow of this additional boundary marginal coupling was in its turn controlled thanks to a cancellation mechanism based on an approximate image rule for the fermionic propagator in the cylinder. Okay, so let me use the last couple of minutes to at least state the theorem we proved back in 2013 with Mastro Pietro on the finite size corrections. So this concerns a situation in which the interaction is ferromagnetic. The domain is a rectangular torus of aspect ratio xi. And what we proved is that asymptotically, as the aspect ratio goes to infinity, the difference between the log of the partition function and its bulk contribution is equal to pi over 12. Here C is equal to 1/2, pi over 12 times xi. Okay, so somehow this theorem gives you a way to compute to compute the so-called central charge of the underlying CFT via the computation of a subleading correction to the log of the partition function. And as expected, this central charge is equal to 1/2, irrespective of the value of lambda, of the term that breaks planarity or integrability of the model. Notice that the bulk term depends explicitly on lambda. So this can be shown quite easily. So the bulk term depends on lambda, but the subleading term does not. And so this is, if you like, the reason why this subleading correction is called universal. The combination of theorem 1 and theorem 2, if you like, prove two remarkable aspects of the picture I mentioned at the beginning for a large class of non-integrable Ising models at the critical point. In particular, they rigorously confirm the picture that the scale limit exists and is given by the conformal field theory associated with the minimal model with central charge 1/2. In theorem 2, the condition that lambda v are positive as well as the requirement xi goes to infinity are technical. As I mentioned, I expect that now that we know how to control certain finite size effects thanks to the refined methods we introduced in the proof of theorem 1 in particular. So now that we are able to compute the scale limit in the cylinder, we have a much better control of finite size correction. So I'm pretty optimistic that as soon as I will have time to sit down and write the proof completely, I should be able to compute the subleading correction fully for any torus of aspect ratio xi without any condition that xi is going to infinity. So to prove the validity of the Ferdinand-Fisher formula for the same general class of interacting of non-integrable Ising model for which theorem 1 holds. So this is strictly speaking unproven, but I'm pretty optimistic that this should be valid for any xi and any lambda v with lambda sufficiently small, but not necessarily positive. Okay, I think I will just skip the sketch of the proof. Anybody who's interested can ask me some details later on, and I conclude with a final slide on open problems. So our methods give us a refined control of the scale limit for energy correlations, but so far we have no control of spin-spin correlations. The computation of the spin-spin correlation corresponds to a partition function in the presence of a string defect. This is the perspective that was used both by Dubeda and by Chelkak, Ongler, and Izurov to compute multi-point spin correlations in the scale limit for the lambda equals 0 case. So the lambda different from 0 case would require to understand the effect of the string defect in the presence of interactions. My vague expectation is that understanding the effect of the boundaries, and in particular of the finite size effect attached to the boundaries, is necessary ingredients in order to understand the effect of these strings that you have to add in order to understand spin-spin correlations. So my hope is that the understanding of the finite size corrections in the presence of boundaries should be related to the computation of the effect of the string defects that should give us information on the asymptotic of spin-spin correlations. But this needs to be done, and it's quite vague at the moment. So far, we have control of even of the energy correlation just in cylindrical domain. It would be nice to compute the scale limit in more general domains. First of all, in rectangles, and even more in domains of generic shape, like the potato-shaped domain I showed at the beginning. This remains to be done, and the limitation of our method in this respect is that our method relies too heavily on the exact solution in the cylinder. The idea would be to perform the multi-scale renormalization group construction without an explicit diagonalization of the propagator, but some technique, I believe that this should be possible, but at the present stage of the state of the art, in a few technical steps, we use certain explicit properties of the propagator that would need to be generalized in the case of generic domains, where the propagator cannot be diagonalized explicitly using an explicit Fourier basis. Last open problem that I would like to mention is that would be very interesting to analyze finite size effect and compute boundary critical exponents in more general models, such as interacting dimers or 6-vertex model or 8-vertex model in the vicinity of their free Fermi point. These models, contrary to the non-planar Ising model, belong to a different universality class when they are outside of their free Fermi point. And so it is expected the boundary critical exponents are different from those at the free Fermi point. And the RG method may be the way to compute this boundary critical exponent. Of course, computation of this boundary critical exponent would require an understanding of the flow of the boundary marginal terms that is something that didn't play any role in the study of our class of Ising models due to the cancellation of the dominant term of this boundary marginal operators that I vaguely mentioned during my presentation. Okay, I think this is more than enough, and thank you very much.
So, okay, thank you, Alessandro, for this very nice talk. I think that we have maybe time for a first question. Okay, I have maybe someone want to ask something or before the next talk. You can use your button of reactions if you no.
Okay.
No. Okay. So if there is no question, let's thank Alessandro again.
Thank you.
And the next, I think, is Sébastien, if I am right. Yes, I am right. So you can share your screen, Sébastien.
Yeah. Is it good?
Yes, tá vendo aí, Ricardo?
You can see the slides.
Yes, yes.
Good.
So the next speaker is Sébastien Ott from University of Genève, and he will speak about interface in the Ising model and their SOS limit, old and new. So it's with you, Sébastien.
Well, thank you, and thank you for organizing the workshop. So I'll talk about interfaces in the Ising model and some effective model to model these interfaces. The talk will be, I hope, non-technical. So I'll show a lot of pictures and a lot of known results and conjectures and a few new things about the model. Okay, so what first are the Ising and the solid-on-solid models? So the Ising model was already introduced by Alessandro. I'll recall it quickly. So it's a probability measure on +1, -1 spins attributed to sites of ZD. And in finite volume, you define it via this well-known formula. And as Alessandro said, I'll focus on this nearest neighbor Ising model, which is one particular Ising model. And you can expect the same type of behavior as I'll describe for like finite range Ising models, but I will not discuss at all finite range Ising models, just the nearest neighbor ones. So otherwise I would have too much to say. So, okay, what do I want to study in this Ising model? Well, first, what are the properties that you can expect? With two properties that will be extremely useful in defining the interface and studying the interface is the notion of spatial Markov property, which is just, if you look at the definition here, the measure in this finite volume lambda that you define using some boundary condition that lives on the whole of ZD. It only depends on eta through sites that are neighboring the boundary of lambda. So you can restrict the boundary condition. If you have one boundary condition on the whole of ZD, you can restrict it to just the knowledge of the sites next to the volume we're interested in. So this is the spatial Markov property. And the other very important object that I'll need is a Gibbs measure associated to the Ising model kernel, that is those finite volumes measures. This finite volume measure allows me to resample the Ising model. If I give you a configuration in the infinite lattice, and I give you a finite domain, this finite volume measure tell me, well, you can resample the configuration inside the domain, given the outside configuration. And a Gibbs measure is a probability measure on the infinite volume configuration that are invariant under all those resamplings. So for any finite volume and any configuration, you can resample the infinite volume Gibbs measure using the finite volume kernel, and this will give you again the infinite volume Gibbs measure. So you can imagine that, like for the Ising model, you can imagine those measures as being limits of finite volume measures. And so the existence follows from the fact that the spin space is compact. And so you can always take subsequential limits of finite volume measures to create an infinite volume Gibbs measure. So the Ising model has a very nice feature, which was mentioned by Alessandro, which is that it undergoes a phase transition in dimension 2 and larger. You have some finite value of the inverse temperature, such that you will have a positive magnetization in any finite volume. However, you can take the boundary conditions as far as you want from your site, and they will influence as far as they want the site inside your volumes. If you are above this transition point, and if you are below, you will have loss of memory on the boundary. Like basically the spins far away from the boundary will be independent of the value of the boundary. If we draw this in pictures, if you are above this beta C, you will find that the boundary, which in my simulation is blue, will influence the whole configuration and will color the whole configuration in blue. While on the other hand, if you are below this critical point, you will have that the boundary will have basically no effect on the configuration well inside my box. So what I wanted to study were interfaces. So we can see that we have basically at least two phases, the plus and minus. In the picture here, it would be the blue phase and the yellow phase. And the yellow and blue are related by a global spin flip. It's just the symmetry of the Hamiltonian. You have a global spin flip symmetry. So if you have an infinite volume blue measure, you also have an infinite volume yellow measure. And these two will play the role of my two phases. So I want to enforce an interface between those two phases. And to do so, well, you need to use boundary conditions. And the most famous boundary conditions used to create an interface are the Brownian boundary condition, which is just you say that you are +1 in half space and -1 on the other half space. So now if you look at any finite volume with those boundary conditions, there will be some form of interface in between those two phases. Making sense of this interface is part of the open problem that I'll mention later. You can use, again, like various geometry. Once you have fixed this infinite volume boundary conditions, you can look at interfaces in a square box or in a half box, and the place where the boundary condition will sit will force like the interface to have different types of behaviors. So let's see like two examples. If you just take the square box, you'll have an interface that fluctuates freely between the two like meeting points of the phase on the boundary. And if you have the boundary of the box is close to your interface, at any scales, the interface will be like forced to live above this boundary layer of yellow sides. You can also define what is called tilted interface, which is exactly taking the boundary, like the half space, to be not parallel to one of the d-1 copies that you have in your system. So you take interface boundary condition interfaces that are not perpendicular to one of the coordinate axes. This will give you what I'll call tilted interface. And all the possible interface you can try to generate via those kind of boundary conditions, they are parameterized by an autonormal vector, which is just a vector in the sphere, which is the normal vector to your deterministic interface that produce your boundary conditions. So what is now the solid-on-solid model? It's a degenerate limit of the Ising model that we'll see what limits you have to take. And it's a probability measure now not on spins, but on heights. So it's really basically you want to mimic the graph interface as the graph of a function. And the SOS model is exactly the probability measure on this graph of functions. So the S model in dimension D will be an interface for the Ising model in dimension D+1. So from now on, I'll always write dimensions as D+1. D will be the dimension of the SOS model, and D+1 will be the dimension of the corresponding Ising model. So in finite volume, you have a certain probability measures on integer heights, so function from ZD to Z. And the probability of a given height function is given by taking the energy to be the absolute height differences. So you look just at the absolute gradient, this gives you an energy. And as we'll see, it corresponds exactly to measuring how many plaquettes in an Ising model are frustrated. Okay, in the same way as the Ising model, we had this spatial Markov property and this notion of Gibbs measure. You can define also the spatial, you can also have that this model, as the interaction depends only on nearest neighbor, you also have a spatial Markov property, and you also have a notion of Gibbs measure because you have the same resampling idea. But now as the spin state is Z, it's an unbounded, so in particular, non-compact space. So the Gibbs measure are not forced to exist. Like it might perfectly be that you don't have any Gibbs measure in a given dimension at a given inverse temperature. And the thing corresponding to the tilted or non-tilted boundary condition, the fact that you can change the orientation of the a priori interface you want to create, like macroscopic behavior of the interface, is parameterized by the slope of the interface, which is just like the asymptotic mean behavior of your interface. So it's a property of the gradient of your measure and of infinite volume measure, and not on the precise height. Like if I have a Gibbs measure for this kernel, I can say that I can shift the whole configuration by an integer. This will still be a Gibbs measure. And the definition of the slope does not depend on the choice of this global shift. So it's really the slope of the deterministic interface I expect to see under a potential Gibbs measure. And so really what you have to have in mind is the Gibbs measure for SOS models with a given slope will be in correspondence with a Gibbs measure for the Ising interfaces in infinite volume with a fixed tilt. So I told you that the SOS model can be seen as a limit of the Ising model. So how do you define first a spin model from the SOS? So here I draw like some SOS interface. So it's just a mapping from Z to Z in dimension 2. And you can create a spin model by just attributing one given spin to all the guys that are above this interface and a reverse spin to the guys that are below this interface, say +1 and -1, which gives you exactly this correspondence with the Ising model, the Bruchian boundary conditions. So here is like a small sample of the SOS interface, and you can look at if you compare with the previous picture, this is very close as the global behavior to what you see in the Ising model. And so the slope is just this you can think of it as just a reparametrization of the normal vector to the boundary condition that you want to construct macroscopically. So the interpolation, what I said is that you can really see this SOS model as a limit of the Ising model. And you do so by, like here in dimension, I'm doing it in dimension 3, but you can do it in other dimension. It's just you say, okay, I take one of the coupling to be like the coupling constants. I took them to be all 1 and nearest neighbor. Now I can change this and I can say, okay, they are 1 if they are nearest neighbor in the first d-1 directions. And if I have a bond which is parallel to the dth coordinate axis, I put a coupling constant j, which eventually can be taken to infinity. And this limit of having one of the coupling constants to send to infinity, this will force all the spins on one column to have, if you look at, okay, maybe with the picture is easier. On each column, you can look at the number of spins that are disagreeing. And this sending j to infinity will force to have at most one disagreeing spin in each column. And you'll have exactly one because of the boundary condition. So you really reconstruct the SOS model by taking this j to infinity limit in finite volume. So you really have an interpolation between the SOS and the Ising model that tells you that somehow the behavior of the Ising model should be well approximated by the behavior of the SOS model. And why do you expect that this SOS model is somehow much simpler than the Ising model? Is that this interface, they make sense for the Ising model at an inverse temperature that is higher than the critical temperature, that is lower than the critical temperature, so beta larger than beta C. And for this SOS model, you can check fairly easily that beta C is equal to 0. So it's really just a statement about statement about the behavior of the interface, or low temperature, very high temperature, very low temperature. They really correspond to something close to 0 or far from 0. While for the Ising model, the questions you want to ask about the interface is close to beta C or far from beta C, which is a priori a much harder question because you don't know beta C in dimension, which are not 2. So what is expected as far as the behavior of those interfaces? So the first thing you can ask is, how do you want to characterize the interface behavior? So from the simulation, you can see it should be some kind of the graph of functions. So first thing you can try to say something about these interfaces is to say, can you define the interface as a d-1 dimensional object. So here D is the dimension of the Ising. So the d-1 is the dimension of the SOS. So can you define like a real surface and prove that in some way this is always close to the graph of a function? If you can do so, you have some notion of well-defined interface. And if you have this notion of well-defined interface, you can ask whether this thing stays very flat or it fluctuates. So once you imagine that you can define a real interface from the Ising model, can you prove that this interface has infinite like diverging with volume variance? So this is a very like complicated statement because you don't even have, for starters, a good definition of the Ising interface. So there are really two parts to this question, which is make sense of what is the Ising interface, and then prove that this Ising interface has a diverging variance. So another way to characterize what one could expect is to go to, in a sense, softer criteria, which is you can look at the Gibbs measure you can obtain, for example, from sending those Dobrushin boundary condition to infinity. You will obtain some Gibbs measure for the Ising model. And the question is, well, if this interface does not fluctuate, like it stays very flat, you will see an interface. If you always look around zero, you will always see this interface. But if you zoom very far away from zero, you'll never see this interface. So you will have a very different behavior depending on the location in space at which you look. Like you'll have deterministically some interface crossing the system at a deterministic place. So you'll have some, that the limiting measure will be non-translation invariant. So this will be a criteria to say that the interface does not fluctuate. If the interface does not fluctuate, then you expect to have translation non-translation invariant Gibbs measures. On the other hand, if the interface fluctuates in an unbounded fashion, whatever the place you look at, if it's fixed in advance, and then you take your volume to infinity, and you only look at that place, you will never see the interface. You will see either that you are in the plus or in the blue phase or in the yellow phase, but you will never see an interface crossing the place because the probability that this interface is anywhere near a fixed bounded regio is zero. So you never see the interface. And so you should recover some form of translation invariance in this case. So this existence of or non-existence of translation invariant measure is heuristically is the same as proving that you have infinite fluctuation in finite volume. So this is another way to characterize a change of behavior in the interface of the Ising model. So if you formulate those questions in the SOS model, it's much simpler because now you have the graph of a function. So in finite volume, the question amounts to say, well, do you have a diverging variance for the spin at any fixed site? While this infinite volume question is, well, if there is fluctuation of the interface, then there should be no Gibbs measure for the interface. Because now the SOS model, if it fluctuates in an unbounded fashion, basically each site will be plus or minus infinity with probability 1/2. And this is not really an interface anymore. So now let me review a bit what is known about those interfaces. Well, for the SOS model, dimension 2 or 1 + 1, so the SOS in dimension 1, so which is an interface in dimension 2, it's very easy in a sense because it's just a random walk. It's a random walk bridge which prescribed endpoints. In any finite volume, the boundary condition will give rise to a random walk with IID steps which have exponential tails. So in particular, it's super easy to compute everything you want about this model. So dimension 1 for 1 + 1 for the SOS model is like now very classical study of random walk. For the Ising model, well, you have this same kind of the interface looks like a random walk, but you have to make sense of what means looks like, and you have to say something more about what is the interface, how to define it, and how to say that it converged to something that is close to random walk. And this was done by Greenberg and Joffe that if you look at this setup of this free interface, so in symmetric box, this converges to a Brownian bridge. And here, I will not say too much about how you prove this result and what I mean by converges to a Brownian bridge, because Yvan will review this kind of convergence in his talk. So he will say a lot more about what I mean by proving an invariance principle for those two-dimensional interfaces. So I will not say too much about how you say what means this statement for the Ising model in dimension 2. And the same, you can handle different types of geometries. This is just an example to say, like, in dimension 2, there is a real understanding of what's going on. You can also prove that in this wall geometry, where now the boundary condition is really close to the interface, so it could influence the measure on the interface, you can also prove this kind of invariance principle, where now the bridge is replaced by an excursion because you have the presence of this wall that conditioned the interface to stay away from the wall. Again, Yvan will say much more about this in his talk. Regarding this infinite volume, like here it was really result in finite volume about scaling limits of interfaces. And what you can say about infinite volume is this existence of translation or non-translation invariant Gibbs states or translation invariant Gibbs states. The first results are by Messager, Miracle-Sol, and Brigmont-Lebowitz and Pfister, that if you take boundary conditions that are like Dobrushin style boundary condition, then you cannot create non-translation invariant Gibbs states. Now, all the Gibbs states you can create via those procedure will be translation invariant. But in fact, in dimension 2, you can prove even more. You can say that any Gibbs state, not only those produced by those Dobrushin style boundary condition, will be translation invariant, and you can characterize the complete set of Gibbs states as they are just convex combination of the two states you can obtain by taking once the blue boundary condition to infinity and once the yellow boundary condition to infinity. And this result was initially due to Eisenman and independently to Higuchi. And then other results, other proofs of this result were derived. I guess an argument by Georgi and Higuchi based on the FKG inequality, and a more recent result by Yvan and Lorraine Coqui. And there they used a more quantitative approach in the sense that they really say that this fluctuation of interface implies that you have, you would never see any interface in the thermodynamic limits. So you need some kind of quantitative statement of this. You never see an interface, and therefore you should never see something else than the plus or the minus phase. So in very high meaning greater than 3, high dimension, what do you have? Well, you have that there the behavior of the interface is in a sense much more trivial, and it should not fluctuate. Like for the SOS model, this is a theorem by Brigmont, Fontaine, and Lebowitz. And this theorem, so here the measure is slightly, it's not fully satisfactory yet as a theorem, but they have to work on the torus. So like the SOS measure on a torus is not exactly well-defined, but it's well-defined as soon as you root one vertex. And then the fluctuation of the interface should be just to look at, if you look far away from that vertex, do you have an exploding or not variance? And this is exactly this quantity, which is you look at the measure on the torus, you can imagine that you root the measure at 0, and you look at the variance at the site, at the distant site x, or you can imagine that you just define the measure as a measure on the gradient of the field, and you look at this difference between two heights squared. And they prove that in this case, you have a finite variance uniformly over the volume. And to do so, they use the fact that you can, on the torus, you can represent the measure as a product of transfer matrices, and they prove an infrared bound using the fact that those transfer matrices are positive definite. So for the Ising model, you expect a similar result, but it's, to the best of my knowledge, still open, that if you are in large dimension at any value greater than the critical temperature, you have non-translation invariant Gibbs states, and they should be obtained from the Dobrushin boundary condition. In the SOS model, which is now So now so this was the result in dimension 3 and higher for the SOS model, so 4 and higher for the Ising model. And what happens now in the most interesting dimension, which is dimension 3 for the Ising or 2+1 for the SOS model? Well, let's look at what happens on pictures. So first, if I look at the picture on the left, it's a high temperature, so small beta value. And on the right, it's a large beta behavior. It's maybe not super clear from the picture because the scales on the right are not so big, but basically on the left, you'll have a fluctuation between -20 and +20. And on the right, you have a fluctuation from -3 to +3. So it's really, you have one picture that is much more localized than the other. And one thing that you can see if you plot a different graph, this will be exactly the same samples, but now I'll plot only the sign of the field. So the blue is 0. The red is strictly positive and the yellow is strictly negative. And here you see that going from very high temperature to very low temperature, you will have some kind of change in the behavior of zeros. Like on the right, the zeros are clearly percolating and forcing the field to stay very flat. While on the left, the zeros are becoming very isolated. And basically you will forget the boundary condition because you just will have some secrets of positive, strictly positive or strictly negative. And you can see that the clusters of strictly positive and strictly negative start to have this fractal look that, well, in fact, should be related to SLE, but that I'll not mention. So what is known about, as far as theorems are concerned, in the SOS model, it's much larger than the Ising model, spoiler. So the first thing is that for large beta, you have a lot, yes, you have a lot which is known perturbatively. And this is the result of Brandenberger and Waynes from 82, and they proved that you have an infinite volume Gibbs measure at large beta and uniformly bounded fluctuation and exponential decay of correlation and everything you like at very high beta. And their argument is a simplification of what I'll say was proven for the Ising model if you just take the special case of the SOS model. They consider various height functions model. Now, if you look still at the SOS model, but the small beta regime, which is the most interesting one, the most difficult one. So the best known, most well-known result on this is the result of Fröhlich and Spencer from 81 in their paper on the Kosterlitz-Thouless phase transition, where they proved there that you have a logarithmically diverging variance for the spin at 0 when you take 0 boundary condition. And well, that's basically the best you can expect at the qualitative, well, semi-quantitative picture. And this method was very recently, I thought it's worth mentioning it. They had, in the proof, they need some symmetry of the field, so which amounts to say that you have a global spin flip symmetry for the height function field. And this prevented them from using, proving the same kind of results when you have boundary conditions that are not 0. So when you want to induce a slope on your boundary condition, on your model, and this problem, this like small defect or drawback of the method was handled by Garbon and Sepulveda in 2020. And the paper of Garbon and Sepulveda is about the integer value Gaussian free field, but the same trick that they use will also work for the SOS model. You have a few changes to make, but from the Fröhlich-Spencer paper plus the argument, you can handle the case of non-zero boundary condition for the SOS model and prove the same logarithmic divergence at very small values of beta. Another very well-known result or family of results on those height functions is the PhD thesis of Scott Sheffield. And there he proved a lot of soft result in the sense that he proves result on the set of Gibbs measures. So not in finite volume, but really on what happens at the level of the Gibbs measures. And he proved that if the slope that you want to reach, like the macroscopic interface that you want to reach, is not a slope that is in Z2, then you never have translation invariant Gibbs states at any values of beta. This is the only result I know about something at any values of beta. And as we'll see, there are conjectures about what should happen at in many cases at any values of beta. And in a recent paper, we proved that you don't have any Gibbs measure at the complement of what Sheffield proved, like at any integer slopes, if you are small enough, like beta is less than log2/8. And this is the result I'll sketch if I have time. Yes, I think I'll have time. I'll sketch at the end the proof of this result. And one of the nice thing I want to mention in any case, so if I don't have time to sketch the proof, you'll hear it anyway, is that in the result of Fröhlich-Spencer and Gardner-Sepulveda, you really have an analytic approach to these results, which is why they get a very strong result, which is a quantitative result on the behavior of the variance. And the result we get is in a sense softer, which is which is existence or not of Gibbs measures. But our approach is really based on this picture here, that you have this percolation of zeros that appears at some value. And we use really this percolation ID on the percolation of level lines, which I think should be one way to attack the problem in a softer fashion than what is done by Fröhlich-Spencer. And finally, like what happens if you have a slope?
Sébastien,
yeah.
Sorry.
Yeah.
Alessandro, just wanted to ask, so when you say at any integer slope, you mean at any integer slope different from 0?
No, any integer slope. Here you have also unbounded fluctuations when beta is small enough.
Beta small enough. Okay.
Beta small enough.
Okay.
Yeah.
Mm-hmm. Okay. Okay. Thank you.
Yeah, the question is very legitimate because beta equals like slope 0 is different. So if now you have a slope, what should happen for the SOS model is that in fact, whenever your slope is non-zero, you should never have an infinite volume Gibbs measure. And the reason is, consider the model at large beta. So here I sampled the model with a slope infinite volume with a slope that is 1/10 and beta, which is large. And you can see that you have the boundary condition, like each color is one height. And you can really see that you have the heights that creates path through the system. Like you really have like fixed height path that create a hierarchy of steps. You have some kind of staircase created by the presence of the boundary condition. And where does the fluctuation come from here? Because you clearly do not forget the boundary, but what you have is that the lines themselves have fluctuations. You can really see it on this picture that you have fluctuation of the lines. How large they will be is very unclear, but these fluctuations of lines should be also of order log of distance. So if you have a box of size n by n, you should have a fluctuation for the central line, which is of order log n, which creates another mechanism to create fluctuation of the global interface. So really this slope case, you have two types of behavior for two sources of fluctuation. One which is the dominant one at small betas, which is that the field itself fluctuates a lot, like for the 0 slope. And the second one, which kicks in at large values of beta, that the staircase that you create by imposing a slope will fluctuate. Like you'll have a collection of lines which will have unbounded fluctuations. Like result on this fluctuation for lines that are conditioned to stay on top of one another, there are some results about the lines related to the dimer models or integrable models of those interacting line systems. So now that SOS is mentioned, what of Ising? Well, here you'll have only one result which is known, and here are two pictures which you should try to relate to those two pictures on the SOS model. So if now you look at this two picture for the Ising model, the right should be at very large beta, so beta much larger than beta C. And you have again that the boundary condition creates an interface that goes through the system. Here I just plotted the plus cluster of the cluster of the boundary condition of the bottom of the box. So you really have that you have this flat structure percolating through the system, while on the left you have this fractal structure that you have really at any place in the system, you have guys that are above this macroscopic interface that you attempted to put through the system, and places where you are below this interface. So you really have this kind of non-percolation of boundary condition going through. So what is expected in this 3D case is that you have a non-trivial roughening transition for the Ising model, which is that there exists a roughening inverse temperature, which is strictly above the critical temperature, such that you have only translation invariant Gibbs states below this beta R, and you have non-translation Gibbs states above this beta R. And this should appear when the normal vector is parallel to a coordinate axis, so really those Dobrushian, non-tilted Dobrushian states that are really the flat interfaces. And again, the same way the non-zero slope of the SOS model, you have this staircase phenomena, you should have the same for the Ising model, which is that if you take a non-zero slope or like a non-tilted interface, a tilted interface, sorry, the interface has unbounded fluctuations and therefore does not give rise to a non-translation invariant Gibbs measure, so that you shouldn't see non-translation invariant Gibbs measure which have interfaces that are not flat. So one part of this result is proved. It's a theorem of Dobrushin, which gave his name to the boundary condition he used, is that beta R is finite, meaning that at large beta, so sufficiently low temperature, you have that this interface produced by the Dobrushin boundary condition will pertain in the thermodynamic limits, and you will have a Gibbs state which accommodates an interface non-fluctuate, with all the one fluctuations through the whole of CD or Z3. And a later proof by Van Byron gave a weaker characterization of this roughening transition. Basically, it does not construct non-translation invariant Gibbs states. He has a result about the correlations that change behavior below certain, above certain value, and that if you believe that you will have only translation invariant Gibbs states below beta R, will predict, well, basically I can tell you the thing is you take this Dobrushin boundary condition, you look at the spin just above the macroscopic interface, and you look at the magnetization above the expected value of the interface or below the expected value of the interface. If it's above, it should be of the same sign of the boundary condition that you put on the top half space. And if it's below, it should have the same sign as the boundary condition in the lower half space. And basically what Van Byron proved is that indeed you have a signed magnetization, which have the expected sign, which is non-zero. While if you believe in that you will have translation invariance below beta R, in the thermodynamic limit, you will have a zero magnetization for those quantities. So it's a weaker statement, but it's a much simpler proof. Okay, and finally, I want to, so do you have questions about the results before I start to present in like 15 minutes the soft result about the roughening for SOS?
Yes, Sébastien. So there is no, so these rigorous results about Ising in 2+1 just concern existence of a non-translational invariant Gibbs state at very low temperature, and well, uniqueness of the Gibbs state at very high temperature. There is no result about existence of two distinct translational invariant Gibbs state at intermediate temperatures, right? So is there so there is no result at all about the intermediate phase. It's just
there is no there is no indication, rigorous indication that beta R is strictly bigger than beta C in dimension 3.
Yeah. Okay. There is no. Okay.
Like at any level, like I think any kind of result would be extremely interesting. But...
Okay.
So, okay, if there are no other questions, I'll go through this I'll go rather quickly through the proof, and if you have questions, you can ask them. So don't hesitate to interrupt. So the idea is really to prove this softer version of the criterion, this infinite volume version of the roughening, which is at small enough values of beta, the SOS model does not have translation invariant Gibbs measure having slope 0. So the result I mentioned is in fact that if beta is less than log 2/8, then you don't have any integer sloped measures, but I'll focus on the 0 slope because it's slightly easier and the IDs are basically all there. So the proof, as I mentioned, rely really on the properties that how heights are percolating through the system, like how does the basically the 0 level line behave. And the second property, that's one property that we used and which is already used by Pete in an earlier work where he works on some specific planar graphs for some larger class of models. So there he has a criteria also for existence of a roughening transition. And here we work on any planar graph, but we restrict to the SOS model, and we will use a property which is really essential and proper to the SOS model, which is very wrong in other models, which is somehow a loss of memory property. So the first things are, I'll use a few tools, so I'll quickly remind them. I think many people are familiar with those, but there is no hurt in reminding them. So the first thing is that if you take a finite volume, you take two boundary conditions, and one of the boundary condition is higher than the other, then you can couple the two finite volume measure in such a way that the higher boundary conditions stay above the lower boundary conditions. And this gives a very simple observation that will be key, is that if you look at a boundary condition which is always greater than some value A, and you are in a volume that contains 0, then the expected value of the site at 0 is at least A. And this is really just, you do a global shift, and then you use the fact that you can put everything to 0 and symmetry of the system to say that with 0 boundary condition, you have 0 mean. Then a second key ingredient is a very deep result from Scott Sheffield in his random surface work. And the result, I stated it for SOS, but it also holds for any height function on planar graphs with convex potentials, is that if you have an ergodic Gibbs measure for the SOS model, which is for the translations, the translation invariant ergodic for translation SOS Gibbs measure, then it's also an extremal Gibbs measure in the sense of extremality of Gibbs measure, which is, in this implication is highly non-trivial. Like if you have a translation invariant extremal measure, it's immediately ergodic, but the other way around is not true, because you could imagine decomposing an ergodic Gibbs measure for translation into extremal Gibbs measures that are not translation invariant. So this result really tells you if you have an ergodic Gibbs measure, you also have an extremal Gibbs measure. And why is it nice that you can have for free, in a sense, extremality, is that extremal Gibbs measures, they have this nice property of being always obtainable through a finite a sequence of finite volume measures with fixed boundary condition. And in particular, they inherit all properties of finite volume measures. And so this property that we had before on the monotonicity of boundary condition leads to the following property on the infinite volume one, which is that if you have two functions that are non-decreasing, in the sense that if I take a height function which is higher than another one, the function will not decrease its value when evaluating it at the higher height function, then these two functions are positively correlated. So example of what is an increasing function is indicator that the site at 0 is greater than some value. And also you have that the one site marginal. So if you look at the marginal on one given site, these guys are log concave, and in particular, they have moments of all orders. So the general idea of the proof is a contradiction, we'll suppose the existence of a translation invariant 0 slope Gibbs measure, and we'll deduce from it some contradicting property. And we'll see what is the contradiction. So the first point is, if you start with a translation invariant Gibbs measure, you can always do a decomposition into ergodic components. You can project it on, like, the ergodic Gibbs measures are the extremal point of the simplex of translation invariant Gibbs measures. So you can always decompose the translation invariant Gibbs measure into ergodic component. So the first thing I do from my translation invariant Gibbs measure that I supposed exists is I extract one ergodic Gibbs measure. Then this Gibbs measure is extremal and so has FKG and have moments. Then I can do a global shift on my height function. This will not change the fact that it's extremal, so it will not change all those properties. Doing an integer shift, I can always assume that the mean value at 0 is greater or equal to -1/2 and strictly smaller than 1/2. If it wasn't so, I could shift the whole configuration by a constant and readjust to fall into this interval. It's very important that this interval is open on the right, so it's strictly less than 1/2, because that's the property we're going to contradict. And in fact, what we contradict is really the integrability of the spin at 0, which is a fairly natural thing to do if you think about it, because it's really what you want to say is that the variance of your finite volume measured blew up, and so that the spin at 0 is non-integrable, does not possess moments. So the second thing, which is where the speculation ID comes in, is a result by Sheffield and also by Dumesnil-Copin, Raufi, and Tassion. There are two different proofs. And that is, if you take a planar graph, here I take Z2, and you color the sites in 2 colors in such a way that each color is FKG, meaning that if I take increasing events on the set of sites that are red, these are positively correlated. So if I take a translation invariant such coloring, then you cannot have a simultaneous percolation of the 2 colors. So with probability 1, you have that you have that probability of red is percolating and blue is percolating is 0. So this is basically telling you that you cannot have phase coexistence in dimension 2, well, in planar graphs. So from this lemma, what can we deduce? Well, we can deduce that if you look at all the heights that are below level 0 strictly, this set does not percolate. So this is just, I will color the spins, and I color red if it's strictly less than 0, and I color blue if it's greater or equal to 0. This gives me a percolation process, so a coloring of the sites. And let's see how this implies that this probability is 1. Well, from ergodicity, the probability of the event is 0 or 1, or by extremality if you prefer. So suppose that it's 0 by contradiction. Then you have that the set where you are lower than 0 percolates. So as it percolates, this no coexistence lemma implies that the set greater or equal to 0 does not percolate. So if you think about it, if you do not percolate this, with the set greater or equal to 0, I can find a cut set of sites where all the sites are less or equal to -1. So with probability 1, I can find such a set of sites. So on a picture, I can find a set of sites that surrounds 0, such that all the guys in the white dots, they are all less or equal to -1. So what I'll do, this is the part, it's not completely trivial, but okay, you can do it, is you can explore this contour from outside. So meaning that to determine which is the contour of less or equal to -1 I want to look at, I only have to look at the values outside of my contour. So once you have done that, you have explored, what you are left with is just, you have a boundary condition where all the sites are less or equal to -1, and you have to sample from this finite volume measure. But by the observation we had earlier, the mean value of the site at 0, when all the boundary are below -1, it's also less or equal to -1. So the mean value for every such contour realization is less than -1. This contour occurs with probability 1, so the mean value of 0 would be less or equal to -1, but we supposed it's greater or equal to -1/2. So this is a contradiction. Therefore, you have that the set of sites strictly less than 0 does not percolate with probability 1. Okay, so now what is the next features, which is this loss of memory feature. So now we have like that this strictly less than 0 does not percolate. And we want to use this to somehow say that we will increase the mean using this fact. So what we want to use is that if I condition now on, so I look at the one spin measure. So I define my SOS measure on just one side. I take any boundary condition on the remainder of ZD or on Z2. Hit this kind of result like the 4, if you replace it by 2D, it's true also in higher dimension. So the probability that a site is greater than 1, given that it's greater than 0, it's always greater or equal to e to the minus 4 beta. And this computation is just the fact that the SOS potential is an absolute value. And then it's exactly the same computation as for probably the loss of memory for the geometric random variables. Here it's just you have to use an inequality instead of an equality at some point, but otherwise it's just a computation of the geometric random variable loss of memory. And this is really the thing proper to SOS model. So this tells you that if you know that the guy is greater than 0, then you can sample it like the distribution, the one-side distribution uniformly over the neighbors, stochastically dominate on this boundary point, on this point, Bernoulli 1/2. If you take beta less than the value that I mentioned at the beginning, which is log 2/4, because it tells you that, well, this e to the minus 4 beta is greater than 1/2. So you really have that. If you have the information that you're greater than 0, you can do whatever you want on the site outside of this guy. You will dominate, this site will dominate a Bernoulli 1/2. So in particular, you can extend it to any set of sites. If I tell you that on a set of sites, I'm always larger than 0, then I will dominate a product Bernoulli 1/2, like independent family of Bernoulli 1/2s. So now how do you use that? Well, if this strictly less than 0 does not percolate with probability 1, I can again find a cut set surrounding 0 where all the heights are greater or equal to 0. So now I explore this contour from outside, and I know that what is the information I reveal? Well, I reveal the site outside of the contour, but on the contour, I just have to reveal the information whether it's greater than 0 or strictly less than 0. So now if I reveal the contour, the conditional measure conditioned on the contour will just be a finite volume measure with some boundary condition, with the conditioned on the fact that all the sites that are like circled in white here are greater or equal to 0. So in particular, the mean value at 0 for every realization of this contour is dominated by a random boundary condition, a random boundary condition sample in finite volume, where the boundary condition are given by IID Bernoulli 1/2 random variables. And now you can just, it's a fairly easy computation. Those Bernoulli 1/2 random variables, you use the symmetry of the Bernoulli 1/2, and you get that the mean value at 0 for this measure with random boundary condition Bernoulli 1/2 is greater or equal to 1/2, which is a contradiction with our assumption that we took the mean value to be strictly smaller than 1/2 at the beginning. So that's really this fluctuation. The fluctuation, once you are sufficiently large, you will fluctuate a bit more. This is basically the small gain at every large enough scales. So, okay, I'll finish by stating a few problems. So I gave a few, the main conjectures. So let me state a few problems that should be easier. So the first one is, in the Ising model, can you define a good notion of interface? Meaning, can you define an object which is really d-1 dimensional, which has order 1 width, and which is approximated very well by the graph of a function? And can you do that for any value larger than the critical beta, any dimension greater than 3, and any kind of tilt you can impose on your interface? A second question is, can you prove a systematic equivalence between finite and infinite volume delocalization characterization? So there is one which is this blow-up of variance for a given boundary condition, and the other one which is this existence of Gibbs measure. So can you prove a generic statement about this. So which would be an analogous of the theorem of Velenik and Lorenz-Cauchy about the Gibbs state in dimension 2, but in, let's say in dimension 2, but for a generic class of model. And in dimension 2+1, you have that the SOS model, if you look at the scaling limit, you rescale the height by the appropriate value, it should converge to the Gaussian free field. Okay, this I did not mention, but this is a priori a very hard question. So, but can you prove that the properly rescaled one spin variants converge? Like, just can you say that if you rescale back the second moment by log of the distance, this converges to a constant? So this would be a first step towards this Gaussian scaling limit. And finally, like in dimension 2+1, we saw that you have this, in the background, you have this percolation of 0, or like almost percolation of 0, some form of percolation of 0 lines underlying the fact that you're localized or not. Can you prove that you have a systematic equivalence between the speculation property of the 0 level line and localization? Like if you don't have percolation, you have delocalization. If you have percolation, you don't have delocalization. You have localization. So that's basically the notion of percolation here is a bit vague, whether it's with respect to the graph structure of Z2 with nearest neighbor edges or with finite range edges. But okay, some notion of percolation of 0 related to delocalization. And I thank you for your attention.
So, okay, thank you, Sébastien. We have questions. Let's see.
Yeah, maybe I can make an additional comment / question. Can I?
Of course.
Yeah, so this is also related to the point 1 of the open problems of Sébastien. Yeah. So one thing that I'm maybe you didn't mention is that if one is at 0 temperature and you consider the 3-dimensional Ising model with tilted Bruchian boundary conditions,
Dimer.
You have an exact mapping into the Dimer model. So at 0 temperature and tilted the Bruchian boundary condition, you have convergence to the Gaussian free field via the non-convergence to the Gaussian free field of the Dimer model. Yeah, it would be, this is something I tried to discuss also with Fabio Toninelli, but for the moment we don't have anything to say about it. So it would be very nice to say that, so with Fabio and Vieri Mastropietro, we studied some interacting versions of the Dimer model and proved the convergence to the Gaussian free field for the height function. So our hope was to include the low temperature Ising model interface in the picture, vaguely
see it as a perturbation of the Dimer.
Yeah, hoping that at low temperatures the effects of somehow of Pyers contours or whatever, of handles or whatever deformations of the surface could be resummed into a sort of effective interaction. But this, okay, but then when we try to define mathematically this effective interaction, we first of all encountered this problem 1. So how do you define because somehow you should project all these excitations on a reference plane or something. I mean, when you have a generic configuration, it's unclear how you should do that, whether you should do this in a sort of weighted way, in a probabilistic way or whatever. And okay, so I would be very interested in understanding whether there is any progress on that.
I think there are two questions. If you want to do this perturbation of the 0 temperature measure, you need something very explicit. So maybe like having a deterministic configuration, like real height function associated to each Ising configuration would be the way to go. But if you look at closer to BTC, when you have a lot of fluctuation and you want to forget all the microscopic detail, there should be some kind of one-step block spin procedure or something very coarse that should work.
Yeah, but I think
which wouldn't work for your problem.
No, but even beta very large would be fine. So the ideal thing for me would be, so of course, if you have a flat interface, you have a convergence of cluster expansion. So somehow the nice thing would be that when things fluctuate, it would be nice to be able to define somehow a restricted class of configurations with a sort of fixed reference surface around which you can prove that cluster expansion for that restricted model converges. So that the whole probability measure becomes a collection of this restricted model, each of which is a perturbation of the reference. Okay, this was the hope, but we didn't succeed in okay, but yeah, maybe it's not impossible. It's just that we didn't find a good way. I don't know.
So, Leandro Chiarini.
Hey, sorry, my question is a bit sillier. Just about problem 3. Is this expected for every beta or?
No, like in a sense, you have to take thermodynamic limits, scaling limits, and somehow beta to. It depends what you ask. Like, but it should be beta to zeros in some sense.
Okay, so you randomize the temperature as well as you're randomizing. Okay, thanks.
So Icasco.
Yeah. So can I? Can I ask a question? So I was wondering about number 4, about the equivalence of percolation of the zero sites and the localization. So how much should this depend on the graph? I mean, if you are, for instance, on a tree, it should probably not be equivalent. Or how do you feel about it? I mean, if you have infinite
I think
clusters of zeros on a tree,
I really expect something in dimension 2, like in anything that is not dimension 2, you couldn't have anything. Like percolation is maybe not the good way to go for higher dimensions. Dimension 2, you have this notion of non-coexistence, which should tell you that the zero level line in some sense is the boundary between the two phases that you don't want to have coexisting. So in a sense, they should percolate because they will constrain the two phase to stay small. And if the two phase start to invade the system, this should stop percolating or take a very fractal structure. So that's just my intuition. That's not clear it's the correct one.
But if you have a completely different graph, like a tree or any other graph which doesn't have a dimension, then it could be completely different. Or what do you have? Okay.
I think on the tree it should be different. Yes.
Yeah.
So if there is no other question or comment, let's thank Sébastien again. Okay. So Lucas, are you there?
Yes.
So you can share your screen.
So is everybody seeing my slides?
Yes. Okay. So the next speaker is Lucas Affonso. He is here from São Paulo, but he's spent 1 year in Canada now. And he will speak about Frog-Spencer revisit, a counter-argument for long-range Ising models. So it's with you, Lucas.
Okay, so I'd like to first thank the organizers, especially Rodrigo, for organizing this conference and for proposing me this problem to study. So let's start. So today I will speak first about a little bit about spin lattice systems. So, so you know what I will be talking about today. After that, I will talk about some historical remarks on contour methods to prove phase transition in long-range spin models. And after that, I will explain the contour argument with these new contours that we introduced based on flux expansion. So today, we will only talk about the ZD lattice in dimensions bigger than 2 with the systems defined by this Hamiltonian that you are seeing. And this Hamiltonian is a Ising-type Hamiltonian. We restrict today to ferromagnetic systems. The coupling constant should be symmetric, and they should be regular, meaning that the sum that you are seeing here over ZD should be finite. So the main examples of this kind of system is the nearest neighbor Ising model, as you saw in Alessandro talk, and the other example that we will focus today is the long-range Ising model, as given by this expression that you are seeing here, for the decaying parameter alpha being bigger than D. So we also introduced a decaying field that was studied in this paper by Sacco, Cassandro, Cioletti, and Presutti, where they studied the phase transition, also uniqueness for the model with the model with a decaying field. And this is the finite volume Gibbs measure, as everyone already spoke here. So if you take the finite volume Gibbs measures and you take the weak star limits, every possible weak star limit, you take the convex rule. This is the set of Gibbs measures. You say that there is uniqueness if by this procedure you only reach one measure, and there is phase transition if you have more than the one measure. For ferromagnetic easy systems, as already stated in this workshop, there is two main examples of measures. The plus is the measure with a plus boundary condition, the measure with a minus boundary condition, and the usual strategy is to show that these two measures are different for somehow. So now I want to discuss an heuristic argument for the phase transition in long-range systems, but in a restricted model with simpler configurations. So first, consider only configurations where you have some ball with a radius r, and where in this ball, inside of this ball, all the spins are plus and the rest are minus. So these are very simple configurations. And if you consider the finite volume Gibbs measure restricted to these configurations, you have this nice formula there. So the usual Pyros argument. To show a Pyros argument, you have to show that the magnetization in the zero is different. So you start using this formula. And in this configuration, for these configurations, it's not hard to see that you have at most R to the D different configurations, because if you see a spin, a positive spin on the zero, then it must be inside some ball, and all possibilities for zero to be inside a ball is approximately R to the D. And you have also that the Hamiltonian should behave more or less like a boundary term, R to the D minus 1. And since we have a modification of the field, we should have this term depending on the field, and also this new quantity here that depends on the long range. It's the long range contribution to the energy, and should be something like that. And so you have this asymptotic behavior for the long range contribution, depending on the decaying parameter, and also you have a control of the decaying field inside inside these balls. So by simply comparing the different exponents, you can guess what's the right picture for the phase transition in this modified model. And this is exactly our theorem, but you don't need to read the theorem. I will just show a picture of what we proved. So if in the x-axis you have alpha minus d, and the other one you have the decaying parameter for the field, the gray region represents the region of parameters where you have phase transition. The dashed line, you have a phase transition for small values of H star. H star for me is always positive. And about uniqueness, we don't know yet. So the problem of phase transitions in these one-dimensional models, as far as I know, started in a paper of Katz and Thompson, where they conjectured that the one-dimensional long-range model should have a phase transition, at least for parameters for the parameter alpha between 1 and 2, including the value 2. And Dyson solved this problem, introducing the hierarchical model, but only for the case for the decaying parameter between 1 and 2. And it was in Froelich Spencer, where they solved the last case, the case for alpha equals to 2, and they based their argument on a previous work on the BKT transition. Is a paper, is a two-dimensional paper for continuous spin models. So after that, you also have many results using these contours. For instance, you have the results from Imbri and Neumann studying cluster expansion. You also have the results of Jonathan studying a similar model for a similar one-dimensional model, but in the let's see gas picture. And after that, as far as I know, for contour arguments, you have this result of Cassandro, Ferrara, Merola, and Presutti, where they extended the contour argument for more general regions of the decaying parameter. So they have to impose an additional condition that the nearest neighbor interaction should be large comparing to the long range contribution. So after that, Letin, Histidis, and Letin, Picot studied. They managed to extend the result for all the region, but since they based their argument on the previous work, they also have this hypothesis of a nearest neighbor interaction being large, and it was in 2019 with Sacco, Endo, Van Etter, Kimura, and Russell, where they managed to prove phase transition, also with a restriction in the decaying parameter. But now the nearest neighbor interaction can be given by 1, for instance. So now for the multidimensional case, you have this result of Genibir, Grossman, and Well, where they managed to show a Pardo's argument using the usual contours, the Ising contours, but they have a restriction in the decaying parameter. It should be larger than d+1. But in their case, they can also manage to prove if you have like a nearest neighbor interaction being ferromagnetic and another interaction being in the long range interaction being antiferromagnetic. If the decaying is bigger than d+1, the argument can also work for this interaction. So after that, we have another result by Park, this time in a much more general context, in an extension of the Pirogov's theory. So it has a more general state space. For instance, it can study the Potts model. But now you have a much more strict condition on the decaying parameter. It should be larger than 3d+1. And Okay, and there is also our result now. And there is a preliminary version available on archive. So what we did, first thing is that we based our construction on the Pyragov-Sinai theory, following parts. So we started following parts. So a core notion for understanding the contours is the notion of correctness and incorrectness of a point. So for a given configuration and a point on ZD, you say that this point X is correct, or it's plus correct or minus correct if all the spins in a ball of radius 1, this means its nearest neighbors, including itself, have the same sign, plus or minus. And the boundary of configuration is exactly those points that doesn't satisfy this condition. So they are let's say, the incorrect points. They are deviations from the plus and the minus configuration. So I can show you a picture. If you look to this picture, and we think that every spin outside this box is in the plus boundary condition, you can extract every plus or minus correct point, and you should get an image like that. So this is the boundary of a configuration. So now, if we follow Pyragov-Sinai, the next step should be given a proper partition of the boundary of a configuration in order to construct the contours. In the usual case, you just break the boundary into connected components, and these are your contours. But in the long range case, since the interaction sees all the lattice, this is not good, because you can have different portions of the boundary, but if they are large, their interaction between them are large. So I have to deal with that. How we do this? So first, we introduce the concept of an MRA partition for the boundary set, and you do this by fixing real numbers M, A, and R for each configuration. Okay, and for each configuration with a finite boundary, you should have a partition that satisfy the following conditions. So first, they form a partition, okay, and they also have this like geometric condition that if you take different elements of the MRA partition, one should be contained in only one connected component of the complement set of the other. So okay, what this means with a picture. If you try to break these two sets, actually, if you try to break this figure that you are seeing there into two sets, gamma and gamma prime, you see that the complement of gamma is all the white regions here. But if you look to gamma prime, you will see that it's actually in three different connected components. This one, and this one. Three different connected components of the complement of gamma. So this is not allowed by condition A. So this is not a valid partition. Oh, I forgot to tell, these examples that I will show are known examples. So you can see what's going on, what can be wrong in the conditions of the MRA partition. So the condition B are conditions related to anti-fragmentation of the contours, and also of the contours that will be, but they are not contours right now, and also a condition on the distances. So first, you take an element of this set, A gamma, And so there should exist a number smaller. It can be at the most 2 to the power r minus 1, and a family you have a family of subsets where you can break gamma into these sets. So the union is all gamma. And for all distinct gamma and gamma prime, you have a condition on the distance. So these sets are well separated. Okay. So a picture now that will illustrate what I mean by these conditions. So first, consider that you have this picture. Now every gray region for now on will be incorrect points. And suppose that you wanted to break your boundary into these two sets, gamma and gamma prime. You have all this distance right here, and you want to know that if this choice satisfies condition B2, and condition B2 is right here for you to see. So you don't forget. For now, let us choose m equals to 1 and r equals to 2. So 2r minus 1 is equals to 3. So what I need to do is to check the condition if there's actually exists as a partition of at most three elements that where the condition of distance is satisfied. So if I consider this as having diameter n, and diameter n, this one now I will put, okay, it's the smaller one, but I will put 3n for now because I want to. So what I have is that if I try to break this set into 3 components, this set right here into 3 components. For instance, you can try to do something like this guy, and this guy. What you see is that the condition on the distance cannot be satisfied, because as you see, this guy is only one element, so I will take the minimum between 3n and n, and then I will have to go to the power a, but the distance is actually na over 2. So this partition doesn't satisfy, and it's not hard to see that there is no way that this can function. It will always break condition B2. So the right guy would be the trivial partition. Just consider everyone as being one element. So okay, but there is also another problem that can happen. For instance, if you look this situation right here, and you try to break this set into, now everything has diameter n again, and this larger one, now we'll choose n squared. So you can actually manage to the condition on B2 of the distance to be satisfied if you take a partition of 4 different elements. So if you do this, you can right away check that you have something like n squared here, the minimum between n squared and n. This is n. You go to the power a, and then since the distance is 2 times n to the power a, this is satisfied. But the problem is that in order to do this, you have to break this hammer set, let's say this hammer, into 4 components. And this is not allowed by condition B1. So this is what I mean by anti-fragmentation. This condition sure doesn't allow you to make too much to break your set into too much different components. So the set that we'll use to construct our contours, they will always be assumed to be the finest one, as in the paper of Felix Spencer. And for us, we will choose a special condition alpha. Oh, not a special condition, but a special value for A that will depend on the interaction. And also the R will depend on A, but in the end of the day, they all depend only on the dimension and on the decaying parameter. So for you to compare, the one dimensional Fourier Spencer model corresponds to a fixed alpha, sorry, to a fixed A 3/2, and the R is equals to 1. And also in the other papers that they have corresponding choices for this parameter. So the thing that is important here is that the condition of the distance have the information of the interaction. So if the interaction is stronger, so you should separate the contours even more, so their interaction is negligible. And also there is another important difference that we more or less follow the Italians in this aspect, is that in this condition here, in the paper of Fourier Spencer, they ask also that the sets should be even. In the corresponding two-dimensional paper, they call this for anyone that read the paper, they call this condition as being neutral. So it doesn't have this here, and also the Italian doesn't have it. So it's okay. You can say that the pictures that I showed you before, I have a trivial partition, and I have another figure that that you don't know exactly how to produce an M-array partition, a non-trivial M-array partition. So the question that you may ask that okay, there is a non-trivial M-array partition. So actually there is one, at least one possibly non-trivial M-array partition. And the idea is based on a multi-scale argument, where at each step we take the boundary configuration, and we have at each step to extract some part of the boundary that is small in distance according to this scale. So I will illustrate this with an example again. So in the first step is the 0th step. You should only look for points. You are only look to the points of the boundary of your configuration, and you should separate them into different sets. If the points have distance less than md to the power 8, so you are separating the connected components, but not only the connected components, also the points that are not too far away. And if the sets that you are collecting the points have less, let's say if A is one of these sets and it has less than 2 to the power A minus 1 points, then you extract them. So for instance, I will consider in this picture only that the set is small enough to not make it to the next step. So the next step, okay, something I need to say, when I say extract, you should extract this painted region here. So let's go to the next step. So in the next step, you just cover the remaining set with cubes of side length 2. You extract a minimal cover, you get something like this. And now you have to extract the sets that are small according to and distance according to the scale. So first thing, you have to to put the cubes, you organize the cubes into of this minimal cover into subsets, such that the cubes have distance smaller than m d to a, and d times 2 is just the diameter of the cube in the L1 arm of these cubes. So okay, and then if they are small, in this case r equals to 3, I forgot to tell you, but r is equals to 3. This means that 2r minus 1 is actually 7. So you take all the collections of cubes that are close together according to this rule. You count them. If you have less than 7 cubes, you extract this guy. So it's not too hard. It's not hard to see that this little guy over here and this guy over here are the ones satisfying this condition. So they will be extracted. Okay, and now we continue. Again, now we go to the next scale. The next scale is 2 to the power 2. So the cubes have side length 4. You always go in powers of 2. You extract a minimal cover, and okay, the same procedure. You have to put the cubes that are together, that are close in what sense? In this case, they should be close to d4 to the power a. Okay, so the condition on the distance changes in its scale. So in this case, it's not hard to see that these are the guys that you have exactly 7. So you will extract these guys. So this is the remaining set. You continue. Of course, you don't have to take anything from a given scale. If this scale doesn't have any small set, any small or distant set, you just continue to the next scale. And now, in this case, you have cubes of side length 16. Now you have exactly 5 cubes, and you extract them. And for this set, the MRA partition should be this guy here, this guy's here, this guy, and this other guy. So as you can see, you can have sets inside other sets. Also, these sets that will be the contours, they can be one inside another, but they have a different feature that they may present some non-connected components. So this may be scary at some point, because you may ask, okay, but now since you have since these sets have more than one connected component, how about the entropy? So I will address this question later, because it's an important question. But now to finish the definition in the Ala Pirogov-Sinai, we can't talk only about the geometry of the contours. We also have to introduce a notion of the labels to talk about the compatibility. And for this, the fact that the sets are not connected impose another problem, because it's not clear that these guys will have all the same label. So, for instance, this is a problem that already appears in the usual Pirogov-Sinai theory. But as you can see, if you take these configurations, then you agree with me that the blue represents the minus spin, and the plus represents the red represents the plus spin. You know that when you go outside from a region of incorrect points to a region of plus correct points, everyone should have the same sign. So in this case, as you may see, this guy have a red boundary outside. This also have a red he also have a red boundary here, but he has it has actually a blue boundary here. So what's the proper definition of label? So if you just erase every hole and just take this one boundary, if we agree with that, then now we have a nice way to define label. But of course, this only have one connected component, and for what you do for the case of the MRE partition. So first, you need to consider only exterior components. So you break your set into connected components. You only take the exterior ones, as in the usual Paulo. And now it's a nice fact that in this case, if you take one element of the MRE partition and you take all of its exterior connected components, they all have the same label. So what is a contour for now? For this case, a contour is a pair. For a configuration of a finite boundary, it's a pair. You have the geometric information that comes from the MRE partition, and you have the label information that we just defined. You also need some other important geometric definitions, like the plus and the minus interior, that as you can see in this figure right here, it has a different feature, because since this, for instance, since this guy here is part of the support, the minus interior, okay, the minus interior, oh no, so the minus interior, that should be something like this, will not include this guy here. So the interior now is only a connected set, not a simply connected set. So it's just a geometric observation. So okay. Also a few more definitions that are important. As everyone knows, this is expected. A contour is external if it's not contained in any other. You separate the sets that are you separate the set of all compatible contours that are exterior. We will call this E lambda plus or minus. And now that we have everything defined, we can go and go back to the question about the entropy of the contours. I will not prove it here. It's on archive if you want to see it. But we can assure you that even if these contours have not only one connected component, they still have a finite entropy. So the condition on the distance is strong enough to guarantee that the entropy is still exponentially bounded, depending on the size of the contour, of course. So, okay. Now for the phase transition, we first have to modify the starting Gibbs measure, because these contours on Pirogov-Sinai, they have since they are based on the notion of correct and incorrect points. If you have for instance, if you are in a plus boundary condition and you put a minus spin exactly on the boundary, you have that all of its nearest neighbors are incorrect. So the contour is not exactly contained on the set lambda. So what you do to not have this problem is just condition your measure to the event that the spins on the inner boundary are compatible with your boundary condition. So okay, we define also now this restricted partition function. Also, we have for a given collection of compatible contours, you have the set of all the configurations that have this particular set that you chose as a subset of its memory partition. And for this given choice, you have the sets that you want to erase. You define this map, this tall map, and the tall. What he do is that it flips the spins on the plus bounded on the plus interior. It erases the support of the contour. It goes everything minus, and it fixes the spins on the exterior volume of gamma. So every other contour that's outside the volume of gamma is untouched. The boundary condition is untouched. Everything that already has the right sign in the minus interior also is untouched. But when you make this spin flip on the plus interior, you are actually preserving the incorrect points, but now you are changing everything that's plus correct to minus correct. So okay, so you can erase the contour and you get a valid configuration, a valid contour configuration. So okay, this is F lambda. We also have to introduce now. At the beginning of this talk, I spoke about something that was related to the contribution of the long range interaction, but only on balls. But since these contours have different geometries, you cannot only study the case for balls. So you have to introduce a more general function. And this is actually the most important result for phase transition. What happens? What's the energy cost when you erase a contour? So this is, but as you may expect, you don't have additivity for the contours as in the nearest neighbor case, but you have a lower bound that's useful for phase transition. This is enough, and you have the following. If you have a fixed contour, only one contour, and you want to erase it, then the difference between the Hamiltonians is lower bounded by the size of the contour as was expected, but also by it has a contribution from the long range that depends on the plus interior. So now to finish this is only a sketch of the proof. You now have the event of the magnetization being +1 on 0. Now you don't restrict to the balls before, and since you are in the minus boundary condition, so you must be inside the volume of some contour. So you have something like this, and using the quasi additivity, now you have this competition here that you should analyze. So okay, and for now, since since you have different geometries, you also have to take care of those components, of those energetic contributions from the field and from the long range, and you actually have these two different regimes for general lambda. First, you have this contribution being lower bounded by something depending on this, and if you change for balls, for instance, you have the right exponents, at least for alpha between d and d+1 and alpha bigger than d+1, and also for the case of the decaying field. So now this is just a computation that you should do. You just compare them using using a right trick. Okay, now we should assume that the sets are large, but you can make a finite modification on the field by putting it to 0 in some parts that will allow you to study the case when the integer is small. So I just put this here because this is the problematic case. So okay, and after that you just conclude as in the usual Paris argument, there is no surprises here. And since you have now the estimation of entropy, you get this is the contribution of the energy. After that you have the contribution, the entropic contribution of the contours. And for beta large enough, this is less than 1/2. Actually 1/2. So thank you. I guess I was too rushed. So does anyone have any questions?
Yes, can I make one?
Yeah,
Hello?
sure.
Okay. Thank you. Very, very, very nice result. Can you please comment so I mean, of course, your contour representation gives you a lot of details. Also in first of all, in some non-reflection positive situations, such as in the presence of this external decaying field, and even in reflection positive situation, I guess you get much more details on the microscopic structure of the Gibbs state. But I imagine that if you're only interested in knowing that there is a phase transition, reflection positivity can be used in some cases to conclude in a sort of soft manner that you have one. For instance, in one dimension, if you only want the Dyson exponents strictly between 1 and 2, you can use reflection positivity without passing through the Dyson argument. And only if you want the critical case alpha = 2, you need to go through the full contour expansion. Is there a similar situation in higher dimensions? So some cases for which reflection positivity can be used to infer phase transition, and other cases where you really need the contour representation.
So okay, we started to develop the contour representation, especially because since you have the decaying field, it's the model is essentially non-translation variant. So reflection positivity is excluded.
In that case, yeah.
But I guess the case for, well, I don't know too much about reflection positivity, but I guess that in high dimensions you have reflection positivity for all the decays, right?
Yeah. I think any decay
you
power
have reflection positive.
You just have to check certain finiteness of an integral. So you have to compute the Fourier transform and compute integrability of the Fourier transform. So, for instance, in one dimension, you have this finiteness for exponent between 1 and 2, and for the decay power 2, the computation is inconclusive. You don't. I mean, you have the bound in the wrong direction.
Yeah.
I guess that there should be something similar in higher dimension too. I just never tried the computation.
Yeah, I think that there is this nice review from Biscup.
Yeah,
on reflection positive. I think he makes this calculation for the long range case.
Okay, in every dimension.
Yeah, in every dimension. But I can't remember the details since I'm not specialist on the technique of reflection positivity. So I can look.
Okay, thanks.
Okay.
One maybe a comment that at some moment we were thinking that maybe the construction could survive to the to dimension 1 also, because for the proof, essentially at some moment to use this parametric inequality, but okay, in the end of the argument, maybe we can jump to dimension 1 also, because in dimension 1 we have this, after Ferrari, the Italian Titi and the people Cassandro and Presutti, they did this paper that modified a little bit the Frog-Spencer argument, but they made this assumption over the first neighbor interaction.
I see.
Yes, we managed to erase it at some moment, but we lost our interval of the interaction of the long range. So maybe we can fix and do for every alpha. I don't know. This was, I don't know.
Okay.
So if anyone else have questions, maybe we should think Lucas again. Okay, sorry.
May I ask about this estimation with difference of the Hamiltonians, like Peirce's argument, Peirce's estimation.
Okay, this one.
Yes. No, okay, this one is also okay, but here is this estimation is much if this C3 and Fi is it? I mean, this last term can be negative, no? This Fi plus gamma.
Oh no, it's always positive because the interaction is it is like this.
I see.
So this
is
ferromagnetic.
No, I see. So this is much more maybe useful than usual Peirce's argument, you know, Peirce's estimation, because in this estimation there was just bounded below by some constant and length of the contour, so you have some extra positive parameter, positive term here.
Yeah, and this is essentially the long range case, because as you see, if you have it can't be the same, it can't be the size of the volume, so it's like this term has a order strictly lower than the order of the volume of the contour. So,
and maybe before last slide you showed that the Peirce's argument works for beta large enough, and there are also some maybe
here.
Yes. So in the last line, so C1 log 2. I mean, this does not depend on beta. Okay. Still, if you take beta large enough, this can be less than 1. Yeah. Yes. Okay.
Okay.
Yes.
Okay.
Yeah.
Okay, actually, I can advertise. I will ask for all the speakers the slides to put on the web page. So I will try to put there if the people allow me. So okay, any other questions or comment? So let's
maybe a last quick one. Do you have comments about a situation in which the long range interaction is as opposite sign? So it is. Instead of being ferromagnetic, it is
anti-ferromagnetic.
You can answer, Lucas.
Yeah, actually, I tried. I actually read your paper in communications, and I tried to do something, because essentially you have to. Because what happens is that you can make. Since these contours are based on Pirogov-Sinai, you can change the definition of what is correct and incorrect if your ground state is periodic. So but once you make that change, everything that has to do with entropy doesn't matter. But the problem is this thing right here, to estimate this.
Okay.
Oh, in your paper you have like you can correct me if I'm wrong, but you have a similar situation where you manage to bound the deviations from the ground state using the number of holes and corners of the configuration, if I remember it correctly. And I couldn't have a similar picture here when I was doing the calculations. But if you change the definition of what is correct and incorrect, you should go to this proposition and try to change to prove something like this with now the new notion of correctness.
Okay, thanks.
Okay.
Anybody else? If not, let's thank Lucas again. So, okay. Tu tem que sair daí, Lucas.
Pronto.
Okay, you can share, Yvan.
Is it okay?
Yes.
You see my slide?
Yes, yes. Okay, so the next speaker is Yvan Velenik from Université de Genève, and he will speak about Ferrari-Spohn asymptotics for an Ising model interface. So, he's with you.
Thank you, and thank you for the invitation and for organizing this workshop. So I'm going to present some recent joint work with Sébastien, with Senya Schlossmann, and with my long-time collaborator and friend Imma-Iofe, who sadly passed away last year. So my talk is about, let's say, the statistical properties of a layer of unstable phase in the two-dimensional Ising model. So we have already had 3 talks about the Ising model, so I will go pretty fast on the definitions, but just I want to fix my notations. So we'll always work in a square box Bn of side length 2n. And first, I will consider the model with plus boundary conditions. So all the spins outside this box Bn are frozen to the value +1, as denoted here. So I denote the corresponding set like that. Then to each such configuration of spin, I associate an energy through the Hamiltonian function, so which I would denote Hn of sigma. And the energy is, as usual, it's the same one you have seen in all the previous talks. There is no magnetic field terms for the moment. It's only the nearest neighbor coupling. And from this Hamiltonian, using the usual recipe, you construct the corresponding Gibbs measure in Bn, which is just a probability measure on the set of configuration which respect the boundary condition, which associate to a particular configuration a probability proportional to exponential of minus the energy of the configuration. Okay. And then, so I've described all this for the plus boundary condition, but it works much more generally for any type of boundary condition that you might fix outside the box Bn. For instance, you could consider the minus boundary condition where all the spins are fixed to -1. And then all the notation extends in a natural way. So for instance, the measure would be denoted mu and beta minus. Okay. Very good. So as we have seen many times today also, this model undergoes a phase transition. So there is a critical value of the inverse temperature beta, which I will denote by beta c, which takes this particular value, such that the following is true. So if you fix a value of beta and you take a box which is big enough might depend on the value of beta, then here are typical configuration inside your box Bn. So the first line is what you see under the measure with plus boundary condition, or say blue boundary condition. I will speak in terms of colors. So the blue boundary condition for the first line and the yellow boundary condition for the second line. Because you see that as long as beta is smaller than beta critical, if you go away from the boundary, so close to the boundary, you can recognize whether you have blue or yellow boundary conditions. But as soon as you go away from the boundary, what you get is close to the center of the box is exactly the same statistically, both under the measure with blue boundary condition and the measure with yellow boundary condition. So the effect of the boundary condition does not propagate inside the box. On the other hand, when beta is larger than beta critical, the situation is completely different. And even if you look at what happens very close to the center of the box, you can recognize which boundary condition was used. And the point being that the effect of the boundary condition propagates everywhere inside the box Bn. So this is a manifestation of the fact that the two-dimensional Ising model, when beta is larger than beta c, can have several different equilibrium phases. Here, the blue phase and the yellow phase. Okay. And what we will be interested in this talk is what happens when you have coexistence, spatial coexistence between these two phases. That is, you want to have them coexisting in the same box Bn. So this is very similar to many of the things that Sébastien discussed in his talk. Okay, so I will impose phase coexistence in the simplest possible way, which is the same that Sébastien explained. So I will use de Bruijn boundary condition. So first, I will use the standard de Bruijn boundary condition where all the spins in the upper half plane have the value +1, and all the spins in the lower half plane have the value -1. But I will also consider a variant of this de Bruijn boundary condition where I impose the plus spins on 3 sides of the box and the minus spins, the yellow spin, on the bottom side of the box. Okay. Now, if we go back to what we saw here, so we saw that when beta is larger than beta c, the boundary condition invades the box, so it propagates inside the box and gives rise to the corresponding phase. We might expect, in these cases, that, for instance, for this first case on the left, we might expect that this blue boundary condition here will give rise to the blue phase in the top half of the box, and this yellow boundary condition here should give rise to the yellow phase in the bottom half of the box with some kind of interface in between. While in this second case, we would expect that since 3 of the sides favor the blue phase should invade the whole of the box, except maybe for a layer along the bottom wall, where one might have a yellow phase. And indeed, that's exactly what happens. So typical configurations for beta larger than beta critical are as follows, provided you take boxes big enough. So we see that for the case of the usual de Bruijn boundary condition, we get the blue phase and the yellow phase separated by a well-defined interface in between. And the second case, the blue phase invades the whole box except for this layer along the boundary. Now, in these 2 cases, the statistical properties of this interface, I mean, the interface at the moment, I will not explain how you precisely characterize the interface and so on. It's pretty obvious from the picture what you want to call the interface in both these cases. But I will explain in more detail later how we really do it. So the statistical properties of these interfaces are very well understood in both these geometries. In particular, it is known that if you make a diffusive scaling of this interface, that is, you rescale horizontally by a factor 1/n, and you rescale vertically by a factor 1/√n, then in both cases, the distribution of this interface or distribution of this interface converge weakly to the distribution of the trajectories of stochastic processes. Namely, for this case, you have convergence to a Brownian bridge, so the trajectories of a Brownian bridge, and here you have convergence to the trajectories of a Brownian excursion. So the Brownian bridge case was proved by Dima and Lev Greenberg in 2005, and the Brownian excursion case was done much more recently in a joint work with Dima, Sébastien, and Vitaly Vartel. In both cases, you can also explicitly compute the diffusive constant of the corresponding Brownian motion, which is related to the curvature of the Wolf shape, which I will denote by chi beta, but it's not very important for my talk. Okay. Now, another issue I would like to explain, because it will be very relevant for what I will say later, is an issue of metastability in this model. Usually, metastability is studied as a dynamical problem. It's really, from a physical point of view, it's really a dynamical problem. But I want to explain a point of view on metastability which makes sense at equilibrium. And it's the following situation. So I consider again our box Bn with with yellow boundary condition, like here. And I will add to the Hamiltonian a new term, a second term, which is a magnetic field term, as you saw in several of the other talks today. So a term which is of the form -h, where h I assume is strictly positive, times the total magnetization in the box Bn, that is the sum over all the spins inside Bn. Okay. Now, since h is positive, if you want to lower the energy, you want to have the magnetization in the box to be positive. So that means that this magnetic field term favors the blue phase. So this term prefers the box to be filled with the blue phase, but obviously the boundary condition that I have applied they prefer to have the yellow phase. I have yellow boundary condition, I would like to have the yellow phase inside. So a priori, there might be a competition between the effect of the boundary condition and the effect of this magnetic field term. Okay, and let's now try to see when one should expect such a competition between the boundary condition and the magnetic field term. So one way of seeing that is by looking at what is the contribution to the total energy that comes from both effects. So the effect of the boundary condition, obviously, the boundary condition only act directly on the spin which are in the outermost layer of Bn, these spins there on this layer, and there are of order n such spins. So the total contribution of the boundary condition to the energy of the configuration is of order n. On the other hand, the magnetic field term, it's coupled to all the spins inside the box, and I have n square, I have of order n square such spins. So the contribution of this term is of order h times n square. So if you want to have a competition between the boundary condition and the magnetic field, you need to have h n square, which is of the same order as n, which means that h has to be of the order of 1 over n. So one would expect that when h is of the order of 1 over n, there is a non-trivial competition between the boundary condition and the magnetic field term. This has been made very precise in the 1990s in a work by Schoenmann and Senya, where they did the following. So they looked at a magnetic field H, which is of the form lambda over n, where lambda is a constant, so it does not depend on n. And then they proved that there is a critical value of this parameter, this constant lambda, which I will denote lambda c. It's strictly positive, it's finite, okay, such that the following is true. So for beta larger than beta critical, the following is true. So if you take a big enough box, here is what you see when lambda is smaller than lambda c. So as long as lambda is smaller than lambda c, so the yellow boundary condition wins, and you get the minus phase inside the box, in spite of the fact that the minus phase is unstable. See, once you have fixed the magnetic field H, say lambda over n, strictly positive, if you take an infinite volume system, then the only stable phase, the only equilibrium phase is the blue phase. But nevertheless, the box is sufficiently small, in this case, that what happens, as long as lambda is smaller than lambda c, what happens is that the yellow phase is metastable and the boundary condition is sufficient to stabilize it. Okay. On the other hand, as soon as lambda is larger than lambda critical, the minus phase becomes unstable, and what happens is that the blue phase invades the system. You see that the blue phase invades the whole box, and you have only a remnant of yellow phase along the boundary of the box. Okay, some small layer of yellow phase. Now that's exactly the issue I would like to investigate and to discuss in this talk, is what can be said about the properties, the statistical properties of this layer of yellow phase. Actually, I'm really interested in the statistical properties of this layer of yellow phase far away from the corner. The reason is the following. So what Schoenmann and Schlossmann proved is that in this case, when lambda is larger than lambda c, if you now take the mesh of the lattice to be 1 over n, and you let n go to infinity, so you take a continuum limit, they were able to describe explicitly what you will see in the box. And what you will see is this. So what you will see is that the blue phase will invade a region which has this shape. It's actually given by, you have 4 arcs here, which are connected by straight line segment along the boundary. And these 4 arcs are quarter of Wolf shapes. Okay. Not that it's very important, but that's what happens. And you still have, even though the yellow phase is unstable, you still have macroscopic quantity of yellow phase in the corner. So what happens in the corner, it's in a sense simpler. It's well understood what happens along this part of the Wolf shape. And what was really not well understood is what happens in this part where you have you are along the wall, and you macroscopically in the continuum limit, you just see a straight line segment. So we would like to understand this. Of course, you want to understand that not in the scaling limit because there is nothing to be seen, but for very large boxes, and see whether we can describe the statistical properties of this layer. Okay. So that's what I want to explain now. So what can we say about the
just a question? And the critical lambda?
Good question. I don't remember what they probably are able to say, or at least today we would be able to say what happens at the critical lambda, but I've not made the computation, so I don't know. I don't know if it was already determined at the time. You need to go to higher order. So what they did, they only treated lambda different from lambda c because they were just doing a large deviation analysis. So they are just comparing the leading exponential term. And this allows you to distinguish between these two situations. If you want to see what happens exactly at lambda c, then you have to look at corrections to these leading terms, which were not available at the time. But now we probably would be able to say what happens at lambda c. But I don't know what happens at lambda c.
May I also ask a question here, Yvan?
Sure.
First question is about this definition of H is lambda over n. How this n can be chosen when you choose the vertex of the lattice? Does it depend on, because
so n is the, I mean, 2n is the size of the box. The side of the box is of length 2n,
yeah,
right?
Okay,
so
then for example, if I take one vertex outside of this box, what will be in the Hamiltonian? What will be the value of H?
Doesn't matter because outside the box, all the spins are fixed to -1. I have yellow boundary conditions.
And inside, everything depends on how far we from zero. Okay, the H.
The H is constant everywhere in the box. The H is equal to lambda over n everywhere in the box.
Okay, so I understand. And then in the right slide, I mean, the picture, if we take lambda is very large, for example, going to infinite, what we can say about the
so when lambda goes to infinity, what happens that this layer of yellow phase disappears?
Disappears?
Yes, because this amounts to having a magnetic field H which goes to infinity, so you have only plus spins. Right?
Okay, yes.
Good.
Okay, thank you very much.
Very good. So I want now to describe what is known about this behavior of this unstable layer, but I will discuss it in a geometry which is a bit simpler than the one that was studied by Schonman and Schlossman. So now I again want to consider this boundary condition where on three sides I impose the blue phase, the blue boundary condition, and on one side I impose the yellow boundary condition, say the bottom side, like in this picture. But again, I'm adding a Hamiltonian to the Hamiltonian magnetic field term of this type. Again, with an H which is strictly positive, magnetic field which is strictly positive. So this magnetic field term again is favoring the blue phase. It wants to have blue spins inside the box. Now, if you remember, when H was equal to 0, I already told you that the blue phase invades the whole box except for a layer along the bottom wall. Okay. So if now I'm adding a term which favors even more the blue phase, then I will still have the blue phase everywhere inside the box. And the only effect of this magnetic field term maybe is to make this layer of yellow phase even smaller than it was before. And that's exactly what happens. So if you fix beta larger than beta c, here is what we had when H was equal to 0. So we had this layer of unstable yellow phase. I told you that if you did a rescaling by 1 over n horizontally and 1 over root n vertically, you had convergence to a non-trivial process, Brownian excursion. This means that the expected height, I mean the average height of this layer, the average width of this layer here was of order root n. Okay, so it's microscopic, but it diverges with n. What happens is that as soon as H is strictly positive, the average widths become of order 1. That is, even if you let n go to infinity, the average width of this layer does not change. It remains of order 1. Okay? So it's really microscopic now. So that's the effect that we would like to understand. What the physicists call pre-weighting is what is the behavior of this guy. And it's a bit annoying because if I want to prove a scaling limit of the same type as those I stated before, say scaling limit to a Brownian bridge, scaling limit to a Brownian excursion, and so on, I need to have something which has a non-trivial scaling limit. But here you have a positive recurrent process along the wall. There is no way I can get an interesting scaling limit there. Okay. So the solution to this problem is to observe that what I can do is that I can take h strictly positive, but instead of taking a fixed value of h, I take a sequence of values of h which are smaller and smaller. So here I've drawn what you see at the bottom of the box for 5 smaller and smaller values of h. And what you observe is that the width of the layer increases as h decreases. Okay. So the hope now is that maybe if when I let the size n of the box tend to infinity, if at the same time I let the strength of the magnetic field H go to 0, then maybe I can get a non-trivial scaling limit for this layer here. And that's exactly what we are going to do. So we choose H as a function of n, and we choose it to be, again, of the form H equal lambda over n, with lambda a positive constant. The reason for this particular choice is to mimic what Schoenmann and Schlossmann did here, because the hope we have is that the geometry you are describing, the scaling limit we'll get in the geometry I'm discussing now will be exactly the same as you get in this case. Okay. So I'm assuming that the magnetic field is of the form lambda over n for a fixed lambda strictly positive. Okay. So such a problem, discussing the properties of this the interface in this situation, has a long history. It has been studied in many works in the physics literature, essentially from the numerical point of view. I will only discuss the mathematical works, and the mathematical works started by looking at something much simpler, which are effective models. So effective models are basically models of the same type as the SOS model that Sébastien discussed today. That is, you want to get rid of all the complication that you have in this model. So for instance, I will forget about all the excitation that I have in the plus phase, in the blue phase, all this yellow excitation there, I want to forget about them. All the blue excitation that I have in this yellow layer, I want to forget about them. And then the complicated geometry of this interface, I want to replace it by something much simpler, which is the trajectory of a one-dimensional random walk. So that's exactly what I'm doing here. So I'm looking at the trajectory of one-dimensional random walk, which is forced to be equal to 0 at time minus n. It's forced to be equal to 0 at time n. It's conditioned to be positive. That's to mimic the fact that the interface in the Ising model cannot go below 0. It cannot cross the wall. So that's a random walk part. And then I want to model the fact that this layer of unstable phase, well, it was unstable. So to model the fact that it was unstable, I'm going to start with the probability that the random walk measure gives to the path. And I'm going to modify it by multiplying this by a density, which is of the form exponential of minus lambda over n, which is our magnetic field, lambda over n, times the area in yellow here, the area of this region, which is delimited by the trajectory and the wall. Okay. And this defines me a probability on the path. Okay. So that's a caricature of what we expect to be rather faithful to what happens in the two-dimensional Ising model. So in this particular setting, which is much simpler, the first work I'm aware of was done in the 1980s by Abraham and Smith. And what they did is that they considered a very specific random walk kernel. Actually, I think it was exactly an SOS kernel, the continuous SOS kernel. So for this very special random walk kernel, they were able to show that the model becomes integrable so that they could compute all kinds of quantities explicitly. In particular, they were able to show that for their specific random walk kernel, the width of the layer was of order n to the 1/3, and the correlation length. So what do I mean by correlation length? So if you look at 2 points here, x and y, and you look at the heights above these points, then you can look at the covariance between these two heights, and this covariance decays exponentially fast. And the rate of exponential decay is given by 1 over the correlation length. So what I'm writing here, you can see it as saying that this rate of exponential decay of the covariance is of order n to the minus 2/3. Okay, so that's what they computed. And then later, roughly 20 years ago, in a joint work with Ostap-Riniv, we extended their results to a very general class of random walk kernels. There you cannot, they are not integrable, so you cannot compute things explicitly, but you can use probabilistic argument in order to prove that what they observed remains true in general. So the width is always of size n to the 1/3, and the correlation length of the order n to the 2/3. So these are really universal behavior. And then finally, the culmination of this line of research was done 6 years ago in a joint paper with Dima and Senya, where we proved that if you rescale this interface in the natural way, so what is the natural way here? Well, I told you that the width is of order n to the 1/3, so you want to rescale vertically by n to the 1/3. And horizontally, the natural length scale is n to the 2/3, so you want to rescale by n to the 2/3 horizontally. Okay. So if you do this rescaling, then we were able to prove that the interface that you get there for these effective models, it converges weakly to the trajectory of a special type of diffusion, which is called the Ferrari-Schwann diffusion. I will say a bit more about that in a few slides. Okay, but there is some specific diffusion to which this converges. So these were results about the effective models. In parallel to these results, there were also works done on the two-dimensional Ising model. The first one that I'm aware of is my work from 20 years ago, roughly speaking, where I proved that the width of the layer in the 2D Ising model is essentially of order n to the 1/3. I had some logarithmic corrections to this n to the 1/3. These logarithmic corrections were removed very recently in a joint work, in a work by Ganguly and Ghessari in 2020, where they proved that the width is exactly of the order n to the 1/3, and they also got various other global estimates about the behavior of the interface in typical configurations. Okay. Now, what I want to explain in this talk is how we were able to extend this convergence to Ferrari-Schwann diffusions from the case of effective models to the case of the two-dimensional Ising model, which provides a complete description of the statistical properties of this interface. Okay. So, but before I do that, I want to explain where this 1/3 is coming from. So why is it 1/3, not 1/2, for instance, that we observe here? And in effective models, it's very easy to understand where this 1/3 comes from, so I will only explain it for the effective model. So it's a heuristic argument. So let's consider an interface of the same type as I described before, one of these effective interfaces there. But I force it to lie between height h and height 3h everywhere over the box from -n to +n. Okay, where h is some fixed number, strictly positive, that I want to optimize upon. Okay, so my interface is doing that. Now, if I want to see what is the contribution of such a realization of the interface, then there are two types of contribution, which come from these two parts of the weight. There is a probabilistic part, a random walk part of the cost, and there is an energetic part of the cost that comes from the magnetic field. So I want to discuss them separately. And let's first look at the energetic cost. So the energetic cost is lambda over n times the area, this yellow area. So what can I say about the area? Well, it will be of order n times h, okay? Because certainly it contains at least this rectangle, and it's contained in this bigger rectangle here. So it's certainly of order n times h. So I get lambda over n times h, which is of order lambda h. So the energetic cost due to the magnetic field is of order lambda h. On the other hand, you have an entropic cost, because the random walk does not like to stay between a layer of size 2h, which it's too narrow, it's not very happy there. So there is a cost to stay there for a time 2n. Okay, what is this cost? Well, it's very easy to guess, say, because for the time your random walk needs to realize that it is stuck inside such a tube of width 2h is a time of order h squared, because your random walk is diffusive. So it needs a time h squared to move a distance h, and it's only in a time of order h squared that it will realize that it's stuck in a tube. So you will pay a cost of order 1 every length h squared inside your tube, and of such pieces of length h squared, you have n over h squared, roughly speaking. Okay, so this will give you the entropic cost. So the probability will be exponential of minus a constant times n over h squared. And now you would like to see when these two costs are equal. So when are the two contribution to the weight of the interface of the same order? So you want to have lambda h of the same order as n over h squared, but this means that h has to be of order n to the 1/3. Okay, this gives you this 1/3 that you want to get. Actually, this argument that I've sketched here, you can really make it rigorous, and that's the basis of what we did with the STAP. We started with something like that. Okay. Now, let me say a few words about the Ferrari-Spohn diffusion so that I can state the main theorem. So it's a diffusion. Actually, it's a family of diffusions. Ferrari-Spohn diffusion is a family of diffusion processes. I will only describe the one which is relevant in our context. So it's a diffusion on R plus with Dirichlet boundary condition at 0. It has the generator which is indicated here. So the usual second derivative part, and then the drift part, which is given by this logarithmic derivative of the function phi 0. Okay, so what is this phi 0? Phi 0 is basically the Airy function. So I've drawn here the graph of the Airy function for those of you who are not familiar with it. So that's what it looks like. It has an exponential decay from positive. Here, it's always strictly positive on this side, and it's only zeros are on the negative axis. And I will call minus omega 1 the first of its zeros along the negative axis, this one. Okay. Then what we do here is that we are recentering, we are translating this Airy function so that this 0 happens at 0. So I'm moving the axis here so that the 0 occurs at 0. Okay. Now, our diffusion is on R plus, so I'm only interested in the part which is positive here, this part. And then there is a rescaling by a complicated constant here, which involves the spontaneous magnetization, it involves the curvature of the Wolf shape, it involves this lambda, which is, you remember the magnetic field is lambda over n, so that's the lambda which appears in the magnetic field. So you have all kind of constant. The point is not to understand where this particular constant comes from, but it's the fact that it is computable. You can explicitly compute this scaling that you have to impose. So we impose this scaling and we get this diffusion here. One other way of looking at this diffusion process is as a Brownian motion that is forced to live in an external potential which has this shape. So it has a logarithmic singularity at 0, which prevents the Brownian motion from reaching the wall. And it has a tail here, which grows like x to the 3/2 on this side. Okay, so that's the kind of effective potential on which your Brownian motion is living. Okay. Now, I would like to say that the interface of the two-dimensional Ising model converges to trajectories of these diffusions, equilibrium trajectories of this diffusion. Now, of course, the trajectories of this diffusion are just functions from R to R, so from R to R plus, actually. So that's pretty clear. But the interface in the Ising model is not of this type. The interface is a mess. So here I've zoomed on a piece of the interface that I drew in a previous picture. And you can see that the interface has very complicated geometry. There are overhangs, it comes back on itself, it does all kinds of complicated things. So it's not clear what it means even to say that it weakly converges to the trajectories of these Ferrari-Spohn diffusions. So one way to make sense of this weak convergence is as follows. I will define two objects which are much simpler, which are the upper and lower envelopes associated to this interface. That is, for each column of spins here, you take each column one at a time, and you will indicate in green the highest point which is below the interface, and in red the lowest point which is above the interface. And you do that for each column. And what you get is something like that, where you see that in most parts, I have the red point, which is just above the green point, which exactly locates the interface. The interface is just in between. That's very nice. But from time to time, you have a gap appearing, and the upper envelope here is really above far above the green and lower envelope, which you have there. Okay, I've drawn in black the bad regions where there is a gap between the upper envelope and the lower envelope. Of course, all these gaps correspond to precisely the places where the interface was not a function, not the graph of a function. Okay, so now how do you deal with that? So this green part and this red part, they are very nice. They are functions from Z to N. So I can easily convert them into function from R to R plus by just making, say, a linear interpolation, for example. So these guys are nice. What is not nice is this, can I really deal with these black pieces? And the point is that you can very easily deal with these black pieces, because what you can prove is the following, very easily. Okay, you can prove that what I'm going to say is true. So as n goes to infinity, with probability going to 1, the maximal height of these black pieces, so the maximal gap you will find, is bounded by k log n. You will not find, with probability going to 1, you will not find a gap which is bigger than k log n, where k is a constant that depends on the inverse temperature, but it's finite. Okay. So the biggest gap is logarithmic in n. Now remember that I want to rescale vertically by n to the 1/3. So the logarithmic gap here are completely negligible. I mean, they will completely disappear under a rescaling by n to the 1/3. Okay? So if I'm able to show that the upper envelope converges to the trajectories of the Ferrari-Spohn diffusion, then the lower envelope will also converge to exactly the same thing, because under descaling, they just become identical, the two envelopes. And since the interface is stuck in between these two envelopes, it will also converge to the same object. Okay, so that's in this sense that we have the weak convergence. So now I can state, say, rather informally here, the main theorem, which was obtained with Dimas, Sébastien, and Senia. And the statement is as follows. So let gamma hat plus be this upper envelope that I drew in red, or actually, in fact, the linearly interpolated function that from R to R that corresponds to this envelope. And then you rescale this guy. I mean, you rescale this envelope by n to the 2/3 horizontally, and by essentially n to the 1/3 vertically. There is again this radius, this curvature of the Wolff-Shape, which appears, but it's not very important. Okay. So as a function of n, you rescale by n to the 2/3 and n to the 1/3. And then you let n go to infinity, and the claim is that indeed the distribution of this rescaled upper envelope converges weakly to the distribution of equilibrium trajectories of the Ferrari-Spohn diffusion. Okay, so that's the statement. And the rest of my talk, I would like to explain, to sketch the proof of this result.
Yvan, may I ask you? Okay, may I ask this question? Very nice pictures like this. How you getting these pictures? Is this computer giving this picture, or is this real some experiment?
It's a numerical experiment. I mean, simulation. It's a
simulation.
very simple simulation. There is not a program which is longer than 20 lines of code.
But simulation is a real. Describing the model, no? And it's
yes,
not
exactly.
just okay.
No, it's
Okay,
an exact simulation of what we want. Yes.
Okay, very good. Thank you.
So the proof is pretty long and technical. It's not easy, but what I would like to convey is the fact that it's very natural. The steps of the proof are all very natural, and from a physical point of view, we are really doing things that should be done. The points you address have to be addressed from a physical point of view. So that's what I would like to try to explain. So let me first start with some simple notations. So here is a realization of a configuration with this blue, 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 yellow boundary condition and this magnetic field. And you see here the interface gamma. And this interface gamma, it's splitting the box into two subsets, one which I will call Bn plus and one which I will call Bn minus, which are these two sets. So Bn plus is here, Bn minus is there. I'm not saying that these sets are necessarily connected. I mean, like Bn minus, you see here, it has a small piece which is disconnected from the rest. Okay, it could be disconnected, doesn't matter. What is important is that if you look at Bn plus, for instance, we know that along these three sides, we have blue boundary condition, but also along the interface, we have blue boundary condition on this side of the interface. So the whole box Bn plus, it has plus boundary condition, blue boundary condition. The same is true for Bn minus. We have minus boundary condition, so yellow boundary condition on the bottom wall. And then along the interface on this side, you also have yellow spins everywhere. So this box fills minus boundary condition, yellow boundary condition, right? So these are my two boxes. Now, the first result we are going to show is some very weak localization statement about this box Bn minus, extremely weak. So we fix some delta, strictly positive, but arbitrarily small, doesn't matter, but you fix it. And then what you can prove is that with probability going to 1 when n goes to infinity, this box Bn minus, it stays inside this rectangle here. So it stays below, so this rectangle has a height delta n, and okay, the length is 2n as before. Okay. So whatever delta you choose, if you take n large enough, then you know that the set Bn minus, so the whole interface stays below this level delta n here. Okay, so that's a very weak localization statement. Actually, one can prove much better, but you see that this will be enough for the argument that I will be giving in a few slides. And in the end, what we are going to prove is that the average height of the interface, actually, we can even prove if we want, that the maximal height of the interface will be of order n to the 1/3. So it will be much better than this delta n. Okay, but to launch the proof, such a very weak localization statement is sufficient. Okay, now the second step is the following. So very well, we have this interface gamma, nice, but gamma is not alone. So there are all kinds of other excitation in the system. We have many of these yellow excitation in the blue phase. We have many of these blue excitation in the yellow phase. These are nasty. What we would like to say is that the effect of all these excitation is just to create an average magnetization in this blue box, this part of the box, which is equal to the magnetization to m star, which is the magnetization of the blue phase, okay? The plus phase. And the effect of this excitation in this box, this yellow box, the yellow part of the box, is to create a magnetization which is essentially minus m star, which is the magnetization of the minus phase. Okay, that's what we would like to say. And one way of making this precise is to show that all this excitation that you have in the blue phase and all these excitation that you have in the yellow phase, they are very small. And very small in a very strong sense. We want to show that all these excitation are all at most logarithmic in n. Okay. Now, sorry, in this part of the box, the statement is almost obvious because it's already true when the magnetic field is equal to 0. When h is equal to 0 in the blue phase, the largest excitation you will find is logarithmic in n. So if you put now a positive magnetic field which favors the blue spins, you will just make the excitation even smaller. And therefore, of course, they will still remain smaller than log. In this part, situation is much more difficult a priori because the yellow phase is unstable. So it might happen that creating a big droplet of blue phase and putting it inside this yellow region here, putting a large droplet of blue phase here, becomes energetically favorable. Of course, you will pay something on the boundary of this droplet because you will have yellow spins close to blue spins. That will cost you something. But then you will have a large area of blue spins here, which are favored by the magnetic field. So it might happen that you gain energy by creating big droplet of blue spins inside this region, in which case you would not, there would be no hope to show that all the excitation are at most logarithmic. Okay, so that's what I want to explain now. That things actually work well. So we want to show that there exists a constant kappa depending on the temperature, such that all contours have diameter at most kappa log n. Okay. As I said, in Bn plus, in the blue part, it's trivial. So let's look at Bn minus, where things are not trivial at all. It's actually a metastability issue that you have to solve. So I will just give a heuristic argument here, but the real proof really follows this heuristic. So let's look how much energy it costs, or how much energy you gain by creating a droplet of plus phase inside this layer of yellow phase. Okay. So to simplify the analysis, I will suppose that my droplet is a square of side length d. So I'm trying to insert a square of side length d inside the yellow phase, and I would like this square to be energetically favorable. So I want to gain energy by inserting this square. So I have to compare two things. So how much does it cost me on the boundary of the square to create it? So the length of the boundary will be 4d. Along the boundary, the fact that I have minus spins next to plus spins, so blue and yellow, which are next to each other, will cost me 2 beta. Okay, so that's the cost of due to the boundary of the droplet. On this side, I have the gain that the interior of the droplet is giving me. So the interior of the droplet has an area which is d square. The gain that the magnetic field will give me will be 2 lambda over n times d square. Now, if I compare these two things and I want the gain to be larger than the cost, then this tells me that the side length d has to be larger than 4 beta over lambda times n, roughly speaking. Okay? Now, remember what we saw earlier. We saw that this box Bn minus gamma lies inside this rectangle of height delta n, where delta can be chosen positive but arbitrarily small. So now I can choose delta much smaller than beta over lambda. Say I choose delta equal to beta over 1000 lambda. Okay. If I do that, then obviously I don't have enough room in Bn minus to insert a droplet which is big enough to be energetically favorable. Okay. So this means, okay, this heuristic argument indicates, and the real proof shows that indeed it's impossible to create a droplet which is what we say supercritical, so which is energetically favorable, which means that the layer of minus phase is actually metastable. Okay, and from this it follows that since there is no contour which is energetically favorable inside this layer, the biggest contour will be logarithmic in L. Okay. So that's an important statement. So that was useful because this allows us, using some old result by Dima and Roberto Schonman from the 1990s, to show that indeed the effect of these phases is to fix the typical magnetization inside the box. So fix a realization of the contour gamma, so gamma is fixed, okay, and look at what we can say about the magnetization in the box. So the magnetization in the box will be up to higher order corrections, which are controlled in this paper, but I will not discuss them here. They are really negligible. The magnetization in the box is given by m star, so the magnetization of the plus phase times the area of the blue part of the box, minus m star times the area of the yellow part of the box, which is exactly what we want, right? Plus higher order terms. And this I can rewrite as m star times the area of the full box Bn minus twice m star beta times the area of the yellow part of the box Bn minus. Okay. I do that in this way because this part does not depend on the contour gamma, so it will disappear in my analysis. Okay. So from this, what follows? It follows that we can get an effective probability for the interface gamma. So here I want to look at the probability of observing a particular realization of the interface gamma at inverse temperature beta, and when the magnetic field is lambda over n. This I can relate to the same probability when h is equal to 0. Okay? And what is the cost of going from there to there? Well, up to higher order corrections, it's given by exponential of minus 2 lambda m star over n times the area of Bn minus. So this lambda over n is the magnetic field, and this 2m star Bn is exactly the one we derived here. Okay? So this gives you an expression which is much simpler for the probability of the interface with the magnetic field in terms of the probability without. And why is it useful? It's useful because when the magnetic field is 0, we know basically everything we want about the statistical properties of the interface. This is due to the Ornstein-Zernike framework that we developed with Massimo Campanino and Dima 20 years ago, and which allows us to couple this interface gamma with a directed random walk on Z2 in a very strong sense, in a sufficiently strong sense that if you are able to control the random walk, then you control essentially completely the interface. I will explain this later. At this stage, the only thing I want to point out is the fact that this random walk that we get, with which we can couple the interface, is a bit nasty because it's spatially inhomogeneous. The point is that if you take an increment of this random walk, then the probability does not only depend on the increment, it really depends on the distance between the two endpoints of the increments and the bottom wall. It really depends on the distance with the bottom wall in a very complicated way. So that's very nasty, and we would like to get rid of this difficulty. So I want to first explain how we get rid of this difficulty. And that's the way we do. So here is a piece of our box Bn. So that's the box Bn. It goes up far away up there, but I'm only interested in what happens close to the wall. And here in red, I have a very small box, which I will call B, this red box here. It has a length which is n to the 2/3 minus epsilon, where epsilon is a strictly positive small number. So I have a length n to the power 2/3 minus epsilon, and a height which is n to the power epsilon. Okay, that's my box B. What I want to show is that when n goes to infinity, with probability going to 1, the interface gamma, which starts here and ends up here, it goes from one corner to the other, this interface gamma will stay above it will never intersect this box B with probability going to 1. Okay, that's what I want to show. Now, the idea of the proof so I want a lower bound. So the point is that you can use the FKG inequality for the following, to prove that you can actually restrict attention to this box C here, which has a length which is twice the length of the red box. So it's 2 times n to the 2 minus epsilon. It has a height which is n to the 1/3 plus epsilon. And how do you do this? Well, you force the interface to pass through the corner of this box, the bottom corner of this box, and the bottom corner on the other side. So through this point and through this point. Okay, and then it continues there. Okay. So you force it to go through here and through there, and then using FKG, you force it to stay inside this box B, this box C. Sorry, this white box. Okay. So that you can easily do. And so now you have reduced the problem to showing that inside this box C, the interface going from this corner to this corner does not intersect the red box. So what have you gained by going from the big box Bn to the small box C? Well, the main problem in this proof is the presence of the magnetic field, because remember that the magnetic field is pushing the interface down. So it's making it more likely for the interface to intersect the box B, okay, because it's pushing it down. So my point is that the magnetic field plays basically no role inside the box C, and that's the reason. Let's see. So what is the area of the box C? The box C has an area which is given by 2 times n to the 2/3 minus epsilon times n to the 1/3 plus epsilon. So this gives you an area which is 2n. Now the magnetic field is lambda over n. So the magnetic field times the area of the box is lambda over n times 2n, which gives you just 2 lambda. It's of order 1. So that means that inside this box C, the Radon-Nikodym derivative between the Gibbs measure with magnetic field and without magnetic field is bounded. So if I have an event which has probability going to 0 when the magnetic field is 0, it's still going to 0 when the magnetic field is lambda over n. Okay. And now I'm done, because when the magnetic field is 0, I have already told you that we know that the interface converges to a Brownian excursion. And using the fact that it converges to a Brownian excursion, you easily prove that you never intersect this box. Okay. Now, actually, you do better than that. Actually, you can compute what is you can upper bound the probability that you do intersect this box. So it's going to 0, this probability, but it's going to 0 sufficiently fast that you can use a union bound to improve the result. And what you get in the end is the following. So in fact, your interface going from there to there will never intersect with probability going to 1, this green box, which has still a height which is n to the power epsilon, but now it has a length which is n to the power 1 minus 5 epsilon. Okay? So it's not macroscopic, it's still smaller than 1, the exponent, but it's much larger than what I need. Because remember that what I want to do is a rescaling, which is horizontally. I want to rescale everything by n to the 2/3. And this is much larger than 2/3 when epsilon is small. Okay, so that will be much more than enough for what I want to do. Okay, so now let me explain how this solves this problem with this, the fact that the effective random walk was not spatially homogeneous. So here is a piece of the interface. That's our green box, the green box which we discussed just before. Okay, we know that the interface stays above this green box. Then the interface continues far to the left and far to the right to reach the corners of the box Bn, but I'm only interested in this part. Okay, and then now at this stage, I want to use this Einstein-Zernike technique that we developed in papers with Massimo Campanino, Dima, and then extended with more recently with Sébastien. And this works as follows. So what we are going to do is we are going to decompose this interface into small pieces, exactly as you see in this picture. So you see that each of these pieces, is lying inside a rectangle. Moreover, all these rectangles are microscopic in the sense that the diameter of each rectangle has exponential tails. So the largest rectangle you will find will be at most logarithmic in n. And moreover, there is a way of choosing the splitting. If you are careful enough in the way you split this, you can actually get statistically independent pieces. This is highly non-trivial because, of course, in the Ising model, this part of the interface is not independent from this part of the interface because there is information which is carried inside the phases, which makes them interact. But there is a way to get a product structure, but okay, that follows from this extension that we did with Sébastien. Okay, so we get now Now all these rectangles are very small. So if I want to control the interface, it's enough that I control these rectangles. And if I want to control the rectangles, it's enough that I control their diagonals. Okay? They completely encode the geometry. Now, these diagonals, I told you that the product is, the measure is product measure, so they are independent. These increments are independent, so I can see them as increments of a directed random walk on Z2, okay, which is coupled to our interface in the way I've just described. Moreover, so as I said before, what is bad a priori is that the probability of this increment does not only depend on the increment, but also on this distance here and on this distance there. But now we know that all these increments lie above this green box, which has a height n to the power epsilon. So they are all very far away from the wall. And then you can show that the effect of the wall, you are so far away from the wall that you can completely neglect the effect of the wall and do as if you were in infinite volume, and therefore you recover a spatially homogeneous random walk. Okay. Now, so where are we? So we have shown that this probability of an interface when the magnetic field is present, you can relate it to the probability when there is no magnetic field up to this prefactor, which involves the area of the box Bn minus. Now, I've explained that this probability when h is equal to 0, you can couple it to the probability of directed random walk on Z2. Now, if I was able to rewrite this prefactor, this exponential prefactor here, so that this Bn minus of gamma, which depends on the realization of the interface, can be replaced by some effective term which depends only on the random walk, then I get here something that I can interpret as a probability measure, a kind of tilted measure on random walk trajectories, which would be a coupling with the original interface when h is non-zero. Okay. So what we do is just the following. So here I have drawn 3 consecutives of these rectangles. In red, you have the interface gamma. The dark gray part is Bn minus. And now remember that this rectangle, the largest one will be log n. The distance between this rectangle and the bottom wall is at least n to the power epsilon. So you're making a very, very small mistake if you replace this area of Bn minus, so this gray area, by the area which is delimited by the path of the random walk, this area in purple that I've drawn, which I call area of x. The error you're making is a higher order correction that will not matter in the analysis. So in this way, you really get a probability distribution and random walk trajectories that is coupled to our original distribution for the Ising interface. So now we are basically done because we have reduced the problem to proving that this guy, this random walk, this kind of tilted random walk measures converge to the trajectories of this Ferrari-Spohn diffusion. But this is basically what we have already done in this earlier paper with Dima and Senya, where we did it for the effective model, because this looks very much like the effective model we were looking at in the earlier paper. So let me just mention a few words what we did in this other paper, the way we proceeded. I don't want to discuss the details because this involves a lot of notations. It's really painful. But the idea is that all the relevant probabilities in terms of this random walk now, all the relevant probabilities, you can, as always, write them as ratio of suitable partition functions. These partition functions, you can very easily express them in terms of a transfer operator, because now it's just a random walk. So if I've already constructed these 2 pieces and I want to add this 3rd piece, then I've just had to multiply by the cost of this increment of the random walk and add to the area here, add the area of this small piece. So it's very easy to construct a transfer operator which encodes everything you need to know about the partition functions. Then you can understand, so this transfer operator, they give rise to a semigroup, and this semigroup, you can understand its asymptotic behavior by looking at the scaling limit of its generator, which can be done completely explicitly. It's just a 2nd order expansion of the generator. You just expand it, and this allows you to compute, to have a very sharp control on large powers of these transfer operators, which gives you a very good control on partition functions. Once you have that, it's enough to prove convergence of finite dimensional distributions, and then a very rough probabilistic arguments just to say that the interface indeed lives on a scale which is roughly n to the 1/3 is enough to get tightness. And with all that, you immediately conclude the convergence to the Ferrari-Spohn distribution that you want. The main difference that we have here compared to our earlier work on effective models is that in the earlier work, we had the space-time trajectory of a one-dimensional random walk. So between time -n and times n, the random walk was making 2 n steps of size 1. Now we have a directed random walk, so it's making a random number of steps of random length. So this means that all this power of the transfer operator becomes random powers. So it adds a layer of technicalities on top of the other paper, but nothing substantial. So the general scheme is just preserved. And maybe just to conclude some open problem in 2 minutes, I'm done. So one thing that would be very interesting would be to consider a magnetic field which does not scale like n to the power -1, as we have done in this work, but as n to the power -α, and show how this depends on alpha. Of course, if alpha is too big, if h decays too fast, what you will get is the same result as if h was equal to 0. So you will just get a Brownian excursion as a limit. It will not be very interesting. But we expect that as provided that alpha is small enough, the result will not depend on the exponent. You will always get the same Ferrari-Spohn limit. And actually, you should get the same Ferrari-Spohn limit if alpha is equal to 0. That is, if you first take n to infinity and then h to 0. Okay. That's the first type of problem that would be nice to study. It's not easy, actually, to study. In particular, this last case where you first send n to infinity and then h to 0. Then the second thing would be nice to extend this analysis from the simplified geometry that we've considered to the original geometry considered by Schoenmann and Schlossmann, this one where you have yellow boundary condition on all 4 sides. We expect that this can be done, and that actually probably there is a way to simply couple this problem with the one we have solved in order to deduce the result for their geometry from the result from our geometry, but we have not yet written down the details, but probably it would work. More interesting, and that's the last thing I want to mention, it would be nice. So as I said, it's pretty well understood what happens in these curved regions where the interface is curved here. It's pretty well understood now, as I explained today, what happens in this region where the interface is flat macroscopically. Okay. The one place where things are not well understood and would be very nice to look at is what happens when this curved piece meets this flat piece. Right here where I have this red dot. Right? Here we expect that depending on how you zoom on this point, you can get any, the fluctuation can be of any size between a square root of n and n to the 1/3. So it's kind of interesting what you can see here, but it's something that we are working on now with Sébastien and Senia, but okay, it has to be concluded. So I thank you very much for your attention.
So, okay, thanks, Yvan. And we have questions or comments.
May I ask some questions?
Yes,
Sure.
of course.
First question is, can we, for example, consider Ising model with 3 spin values, not with 2? And then, for example, for yellow color, you have, blue color is very dominated in boundary. If you have 3 color, for example, and maybe if they have somehow, for example, yellow and red is proportional to, say, blue color in the boundary. Maybe somehow they will dominate. This some of these 2 colors will dominate this blue color. Can we somehow investigate this kind of phenomenon?
So models with more than 2 colors are, of course, very interesting. These things have been studied by physicists. So there is something they call interfacial adsorption, where you look at Dobrushin, say, between, I don't remember the colors you use, but say blue and yellow, but you have also a color red. And blue and yellow are both stable, but the red color is unstable. And what might happen is that at the interface between blue and yellow, you might create a layer of red because it might be favorable to go from blue to red to yellow rather than directly from blue to yellow. So these kind of things are very interesting. Problem is that there are very few models with more than 2 colors for which you have all the tools necessary. So possibly in the POTS model, we could do something.
I see.
But for a Blume-Capel, for example, which would be very natural for this problem, we don't have the correlation inequalities that we would need and the representation that we would need, probably. But maybe for Potts model, we could do something.
Leandro?
Hi, thanks for the talk. I don't know if my question is silly, but I know that, well, in dimension 3, the surface is rigid, but would you still get something non-trivial if you put a field that is decaying at the right, is there a right speed for which you see something interesting?
Yes. Yeah, so I did that for effective models. So for effective models, you can say take a Gaussian free field, and you model this for as a surface, and then you tilt it with exponential of minus lambda times the area between the volume between this random surface and the wall, and then you can indeed you get indeed an interesting behavior. So I think in dimension 2 you get a logarithmic divergence in lambda, and in dimension 3 and higher you get square root of log. Okay. So you get interesting behavior. So no power law. It's always logarithmic or square root of log, but you get something indeed. Okay. But for the Ising model, we would have no idea how to do this, of course.
Okay. And sorry, this question is a bit more open, but in this spirit of taking the right size of the magnetization field, if I get the Ising model on a torus and I put a magnetization field which decays with its plus h over n, and in the lower half it's minus h to n, you still see the same kind of behavior as well for the de Bruijn interaction. Does that make sense? I'm taking out the
Yes.
Oh, okay.
So my guess is yes, yes. So I expect that you would get the same. So the limiting process would not be the same. It would be another Ferrari-Spohn diffusion. Okay. Because you get something which is there is no hard wall now. So you can the interface can deviate both upward and downward, but it will be the exponent will probably be the same. So you will still get the exponent 1/3 in this case, but the process itself is a process on R, not on R plus. The diffusion is on R now, and it's a generalization of this diffusion that I'm discussing here.
Are those diffusions?
We have not done it, but probably we could.
Okay. But sorry, it's just because I'm not familiar with this family of diffusions. Are they well understood in terms of it's parameterized in terms of a function, right?
Yes.
Or, no, okay. Are they well understood?
You have a Sturm-Liouville operator behind, and so this Sturm-Liouville operator, they have a potential part, if you want, and it's parameterized by this potential part. So what function you take for potential? In our case, for the case relevant to this talk, the potential part is just a linear function.
Okay.
But you can take anything else, and you get another Ferrari-Spohn diffusion. And some of these are indeed they are appearing in other contexts.
Oh, okay. Well, thank you very much.
Welcome.
Okay. So
may I ask a question?
No. Is Yassini talking?
No, can I ask a question first?
Okay, go ahead, Yassini.
Okay, no, just my question is, I'm not sure if I missed it or not, but when the last open problem you mentioned in this corner of the box, so yes. You said, what are you expecting as behavior?
Here?
Yes.
Well, the fluctuation will be root n with diffusivity constant, which will be given by the curvature at this particular point. So these things have been done by, at very low temperature. Non-perturbative proof has not yet been done. It would be accessible today. We would be able to do it, I guess, today, but it was done at very low temperature more than 20 years ago by de Bruijn and Remy. So it's a Gaussian process with and the diffusivity is related to the curvature of the curve. Yeah.
Okay, thanks.
Okay, go ahead, Leandro.
Hi, Yvan. Thank you very much for this nice talk. I was wondering if the techniques you present could be handle a similar problem like this. You put plus boundary condition outside and frozen inside with minus boundary condition. I thought that the local analysis you presented would be similar in this region. can you say something about this problem?
So I'm not sure if I've understood what you have. You have two squares, one inside the other?
Yeah.
That's what you're saying? Yes, one with plus boundary condition, the outermost is plus boundary condition, and the innermost is minus.
Yes.
And then you have an interface separating the two, right? That's
yes.
what you want to say.
Yes, and
yes,
I thought that.
In principle, the technology we have allows to treat this kind of situations. Now, one would have to look at it precisely to be sure that there is not something that prevents us from writing a proof. But in principle, the technology allows to study these kind of problems. Yes.
Cool.
Okay, anybody else? Comments or questions? No? So let's thank the Yvan again and all the speakers. Thanks a lot for coming, people.
Thank you for organizing this.
Yes, and thanks Rodrigo for the organization.
And also Ricardo Freire, that is my friend, that he helped me with the technical part and do everything.
Okay,
thank you.
Okay, so see you in person in the future, I hope.
Let's hope, yes.